Most of the numbers we deal with in daily life are small. Even the biggest ones, like the distance to another city or the time it takes to finish a school year, still fit inside a mental box we've carried since childhood. But the moment we try to scale that box up to the universe, everything goes sideways. Our intuition collapses. Distances stop feeling like distances. They turn into strings of digits that carry no weight. A light year is one of the first places where this happens. On paper, it's simple. It's just how far light travels in a year. But light moves so fast that the number feels fake. You can write it down, about 9.46 trillion kilometers, but that doesn't help because our brains never evolved to picture anything even close to that size. We can imagine a road trip. We can imagine a continent. We can't imagine a beam of light sprinting non-stop for 12 straight months. And yet astronomers use light years the way we talk about minutes or meters. To them, it's practical. To us, it's like someone casually describing their morning walk as 3 billion sandwiches long. The unit is real, our intuition is not. So today we're going to unpack what a light year actually means, why it breaks our sense of scale, and what happens when you stretch that idea across the Milky Way and beyond. This is where distance itself stops behaving the way we expect, and where our normal mental tools finally run out. If you've ever tried to picture an astronomical distance and felt your mind sort of slip, you're not alone. There's a reason the numbers feel heavy, but the meaning feels hollow. Our brains didn't form in a world where trillions of kilometers mattered. They formed in a world where judging the distance between one tree and the next helped you survive. You didn't need to imagine anything larger than the horizon, and you definitely didn't need to picture the space between stars. That's the first big barrier. Our sense of space evolved for a scale we could physically interact with. When you're dealing with everyday objects, distance is intuitive because you can couple it to movement. If you want to reach a cup, you extend your arm. If you want to cross a room, you walk. If something's far away, you can perform a simple check in your head. If I left now, how long would it take to get there? That question works for human-sized distances because walking, driving, and even flying give you enough feedback to build a stable internal model. You ask your brain for a distance, and your brain answers with a sense: near, far, long, short. It doesn't need the exact number. Cosmic distances don't work like that. They break the connection between distance and experience. You can't walk to a planet. You can't drive to a star. You can't gather memories of anything remotely close to a light year because nothing in life requires you to move through an empty void for years at extreme speed. When that link disappears, the link between movement, time, and physical size, your intuition has nothing to latch onto. All that's left is a raw number, and raw numbers feel abstract. Here's a simple example. Think about the distance to your nearest grocery store. A kilometer? Maybe 2? Even if you've never measured it, you have a sense of it because you can picture the route. Now, think about the distance to your nearest neighboring city. That's bigger but still manageable, because maybe you've driven it. Your memory fills in the scale with familiar landmarks. But now imagine asking yourself, how far is 50,000 kilometers? That's more than the circumference of Earth. Nobody has walked that, driven that, or flown that in one go. You can write the number down. You can compare it to Earth size. But your brain doesn't light up with a feeling of scale. It just stores it as big. Now stretch that big to trillions. The sense of distance doesn't just weaken, it collapses completely. And once your intuition collapses, you can't rebuild it using everyday logic. The numbers outstrip anything you've ever lived. Another problem is that our mental number line is deeply compressed for anything huge. We treat large quantities in broad strokes. When you hear 1,000,000 and 1,000,000,000, the difference is enormous, 1,000 times, but mentally they occupy almost the same category. A lot. Humans are great at estimating ratios on small scales. We can tell the difference between 5 apples and 10 apples easily. But we're terrible at distinguishing between 500 million and 800 million without training. Everything past a certain point blends into a single mental bucket. Big is big, bigger is also big. Our brain doesn't naturally care about the scale difference because both are outside our survival range. This compression kicks in even harder with distance. Instead of giving us a sense of scale, the mind gives us a label. That's really far. The problem is that really far can describe something 500 kilometers away, or 50 light years away, even though those two distances don't exist in the same universe of meaning. One is a tough road trip. The other is a gap that light itself needs decades to cross. But because we have no experience with distances spanning years of travel at the fastest speed possible in the universe, the brain stores both under the same mental tag. Astronomers work with these numbers every day, so they get used to seeing them. But they're not intuitive to them either, not in the everyday sense. They've just built mental shortcuts. They compare one cosmic distance to another rather than trying to force intuition where it can't exist. You can't picture 1 trillion kilometers, but you can say one star is 4 times farther than another and work with that relationship. Humans are good at relative comparisons, even when the absolute values escape us. Another reason these distances break our intuition is that space isn't filled with landmarks. When you're on Earth, you use objects to judge scale. Buildings, mountains, trees, rivers, they all give you references that help your brain calibrate what far means. Outer space has none of that. Everything is so spread out that you can't build a mental path between objects. The distances are too large, the in-between is too empty, and the objects at either end are too faint or too small in your field of view. If you try to visualize the distance from Earth to Mars, most people picture a straight line between 2 bright dots. But that picture hides the empty volume between them. The gap is not a few finger widths on a browser diagram, it's tens of millions of kilometers of nothing. And because nothing has no features, the mind compresses it all into something that feels tiny and symbolic. Once again, the numbers don't feel real. There's also a language barrier. Human languages weren't built for cosmic scales. Words like trillion, quadrillion, or light year aren't tied to concrete experiences. They're symbolic noises. When you say 5 meters, you can picture 5 meters. When you say 5 light years, no linguistic instinct kicks in. You're simply repeating a technical phrase. You might know the definition, but the word doesn't hook into any physical memory. And without memory, you can't form mental scale. Even time breaks down. We're good at thinking about minutes, hours, and maybe months. Once you hit a decade, the human brain starts blurring things together. Now try thinking about the time it takes light to cross the Milky Way. Roughly 100,000 years. Humans can barely picture 200 years of history without relying on books, let alone 100,000 years of continuous travel. Our entire sense of historical time collapses at those scales. Humanity's oldest cities haven't even existed for 1% of the time it takes light to cross our own galaxy. All of these limits pile up. No reference points, no experiential anchors, compressed number sense, language that doesn't map to physical intuition, and a total lack of movement-based experience. But there's a deeper problem underneath everything else. The universe operates on scales that don't matter to our survival. Natural selection shaped us to solve problems in forests, plains, caves, and small communities. Not in star systems, not across galaxies. The entire cosmic scale is irrelevant to whether a person survives their day. So our brains didn't invest in the machinery needed to comprehend any of it. This is why cosmic numbers feel like they bounce off your mind. You try to picture them, but nothing sticks. It's not a flaw, it's simply a mismatch between the world we evolved in and the universe we're trying to understand. Even astronomy educators run into this every day. When someone hears that the moon is about 384,000 kilometers away, their first reaction is usually that it sounds reasonable. But if you tell them Earth is only about 40,000 kilometers around, so the moon is almost 10 Earth circumferences away, suddenly the number feels strange. Same distance, different framing. That's how fragile our intuition is. Change the reference point and the whole feeling of scale shifts. This is also why scale models help, but only up to a point. You can shrink the solar system down so Earth is a marble and the Sun is a basketball, and that can help with proportions. But the distances between those objects still end up so large, even in a model, that you usually have to place them across a football field. And even then, you lose the sense of emptiness between everything. A marble on one end of a field and a tiny bead on the other don't recreate the experience of a star system. They're just objects placed arbitrarily far apart. Your brain sees 2 things on a field, not 2 things separated by tens of millions of kilometers. Real space doesn't give you grass or lines or goalposts to frame scale, so the model fails to anchor the experience the way we want. There's also a limit to analogy itself. We often try to explain cosmic distances by scaling down the universe to something familiar. If the Sun were the size of a ping pong ball, or if the Milky Way were the size of a pancake. These analogies help with relationships, but they're terrible at conveying the raw distance. They don't give you the feeling of traveling through that distance. And the feeling is what we lack. You can shrink Earth down in your mind, but you cannot simulate what it means to travel 1 trillion kilometers, because your brain has no concept of continuous motion at that scale. You can only gesture at it abstractly. You can count, you can compare, but you can't feel it. So when astronomers use a unit like light year, the problem isn't that the definition is confusing. The problem is that the concept demands a kind of spatial imagination that the human brain simply doesn't possess. This is the distance light travels in 1 year, is a clean statement. The difficulty comes from imagining what that travel actually looks like. Light never rests. It never slows down. It moves faster than anything you've ever encountered. Not just faster than a jet or a bullet, faster than your mind can picture as motion. Try imagining something crossing the continental US in a few thousandths of a second. You can do it as a number, but as an experience? Impossible. Now multiply that impossible speed by 31 million seconds, the number of seconds in a year. The result is a distance that no human experience can touch. That's why the unit light year becomes symbolic the moment you learn it. You know the definition, but you can't map it to sensation. And without sensation, it becomes a placeholder for a distance too big for me. The strange irony is that our universe is shaped almost entirely by phenomena that happen across distances we cannot imagine. Galaxy clusters pull on each other across millions of light years. Cosmic filaments stretch for billions of light years. Even the shape of the Milky Way depends on how matter is distributed across tens of thousands of light years. These large-scale structures are real, measurable, and deeply important. But none of them are real in the way your living room is real. You can't walk across them. You can't turn your head and see them in perspective. You can't feel them in your body, and that's why cosmic distance breaks our brains. It disconnects the number from the experience. The human mind is extraordinary at pattern recognition, storytelling, and problem-solving, but it's not a tool built for absorbing distances that require light, a universal speed limit, to spend years, centuries, or millennia traveling through emptiness. Understanding this doesn't make the distances feel any smaller, but it does make them easier to think about. If your intuition collapses the moment you go beyond Earth-scale distances, that's exactly what it's supposed to do. And the rest of this episode builds from that. Once we unpack what a light year truly represents, we can finally start making sense of the distances that stretch across star systems, galaxies, and the entire observable universe without pretending our brains were designed to picture them. When most people hear the term light year, they instinctively think of time. It makes sense, the word year is right there. And if you're used to sci-fi shows tossing the term around as if it's just futuristic slang, it's easy to imagine it as some sort of countdown or travel duration. But a light year isn't time at all, it's distance. One very specific distance defined by the fastest thing in the universe, moving non-stop for 1 full year. To understand why we use it and why it shows up everywhere in astronomy, it helps to break it down into the pieces your mind actually can grasp. The speed of light, the length of a second, and what happens when you multiply that speed by the sheer amount of time in a year. Start with something intuitive. Speed is just distance per time. When you walk, maybe you move a meter in a second. When a car drives on a highway, it might travel 30 meters every second. A fast jet can push past 300 meters per second. These speeds feel tangible because you've seen them, felt them, or at least watched them happen. Your brain knows what a car rushing by looks like. Light is nothing like that. Light doesn't look fast because you never get to watch it move. The moment a light switch flips on, the room brightens instantly to your eyes. There's no delay, no visible travel, nothing that feels like movement. So when someone tells you light travels at about 300,000 kilometers per second, your brain has no experience to plug that into. A car is fast, a jet is very fast. Sound is unbelievably fast. But light is so far beyond anything in your daily life that the word fast stops describing it. It becomes something else entirely. Still, let's hold on to that number. Roughly 300,000 kilometers per second. More precisely, 299,792 kilometers per second in a vacuum. You don't need the exact digits to build intuition. It's the scale that matters. A single second of light travel is already enormous. If you could ride a beam of light for just 1 second, you'd circle Earth more than 7 times. That fact alone starts to stretch intuition, but it's still manageable because Earth is familiar. What becomes harder to picture is what happens when you let light keep going. Imagine a timer. 1 second, then 2, then 10, then 100. Light has now traveled something like 30 million kilometers. That's nearly the distance between the Earth and the Sun at its closest point, a distance that already feels like an abstraction. But in astronomy, we don't measure things in seconds, minutes, or hours because those units crumble under the amount of space involved. So we bring in years, not because we're thinking about time, but because a year is simply a convenient chunk of seconds. A year has around 31.56 million seconds. Multiply that by the speed of light, and you get the raw distance defined by a light year, about 9.46 trillion kilometers. This is where the trouble begins. When you hear 9.46 trillion kilometers, unless you happen to run spacecraft navigation for a living, that number doesn't mean anything. Not in the sense of, I can imagine that. It feels like saying a lot. But the number does have meaning, and we can tease it out by stepping through smaller slices of it. Start with a light second, roughly 300,000 kilometers. That's almost the distance from Earth to the Moon. Not exactly, but close enough to visualize. You could say the Moon is a little more than 1 light second away, which means if something happens on the Moon, a burst of light from a laser, for example, you won't see it until about 1 second later. This isn't a delay you can feel in everyday life, but it's real. Now, jump to a light minute. There are 60 seconds in a minute, so multiply by 60 and you get about 18 million kilometers. That number is already hard to anchor, but you can tie it to something real. It's about how far light travels from the Sun in that time. The Sun is roughly 8 light minutes away from Earth, so when you look at the Sun, ideally not directly, you're seeing it as it was 8 minutes ago. If the Sun vanished instantly, which it won't, you wouldn't know for 8 whole minutes. These steps are important because they show how fast the scale stacks. 1 second is the Moon. 1 minute is the distance to the inner parts of the solar system. 1 hour? That's 60 light minutes. Light traveling more than 1 billion kilometers. Once you reach a full day of light travel, the numbers get surreal. Light would go far beyond the orbit of Neptune in a single day. Think about that. Every planet you've ever heard of, every spacecraft humanity has launched, even the farthest probes, all would be left far behind by light in just 24 hours. Now stretch that travel over a year. Light doesn't slow down, it doesn't get tired, it doesn't stop to refuel. It just goes relentlessly through empty space. The final result, 9.46 trillion kilometers, isn't designed to be intuitive, it's designed to be useful. But why define a unit this way at all? Why not stick to kilometers? The shortest answer? Practicality. Once you're outside our solar system, kilometers become almost useless. If you try to express the distance to the nearest star in kilometers, you end up with a figure so long that it becomes unreadable, and repeating it doesn't teach you anything. Instead of clarity, it gives you noise. Scientists needed a way to describe cosmic distances with numbers that were still meaningful. But there's another deeper reason. Light connects time and space in a way nothing else does. Because its speed is constant, light becomes a natural measuring stick for the universe. When you measure distance by light travel, you're also measuring a kind of history. If a star is 10 light years away, you're seeing it as it looked 10 years ago. If a galaxy is 100 million light years away, you're seeing ancient light, emitted long before humans existed. Distance and time merge, one explains the other. This dual meaning can cause confusion because a light year feels like it describes how long something takes to travel. Technically, light can cross 1 light year in 1 year because of how we define the unit. But if you tried traveling that same distance, even at the fastest speeds humans have ever reached, it would take tens of thousands of years. So even though the term includes year, it isn't telling you a ship's travel duration. It's only describing the length of the path. A seasoned astronomer hears light year the same way you hear mile. It's a distance, nothing more. But unlike miles, the hitch is that you can't imagine walking or driving that distance. You can't stand at the start of a light year and look toward the end. There's no frame, no road, no physical sense of scale. That's why, even though the definition is straightforward, internalizing it is hard. To make the unit feel less alien, you can compare it to other common cosmic distances. For example, the diameter of our solar system, meaning the span across which the sun's gravity dominates, is roughly a couple of light days. Even the giant orbit of far-off icy objects like those in the Oort cloud sits comfortably within 1 light year. So the entire solar system, enormous as it is, fits inside a single cube whose edges represent 1 year of light travel. Stars are spaced so far apart that the Sun's nearest neighbor, Proxima Centauri, sits around 4.24 light-years away. That may sound like a small number given the scale of the universe, but think about what that means. If you could ride on a light beam, it would still take more than 4 years to get there. Compare that to Earth. Light crosses the entire planet in a fraction of a second. That contrast alone shows why the unit is so valuable. It compresses the unimaginable into something that fits in a sentence. But the simplicity hides the depth behind it. A light year isn't just how far light travels. It's the maximum distance information can travel in that time. Nothing can outrun light, so nothing can cover a light year in less than a year, unless it's hypothetical or fictional. When astronomers use the term, they're implicitly talking about causality, communication, and the structure of space itself. That's why the unit appears everywhere in astrophysics. It's tied to the rules of the universe, not just a convention. For example, imagine 2 stars separated by 10 light years. If something dramatic happens on one star, a burst of energetic radiation or the collapse of a companion, it will take 10 full years before the event can physically affect anything near the other star. The distance isn't just empty space, it's a delay built into the universe. This connection between space and time is why light years work so well for describing the cosmic landscape. The same distance also marks how old the information is. When astronomers look out at something 500 light years away, they're peering into the past by 500 years. Space and time aren't separate ideas in practice. They blend because of how light behaves. But none of this helps if you're still struggling with the scale of 1 trillion kilometers, so it's worth taking a moment to break the light-year distance into something more digestible. Imagine laying down rulers end to end. A typical ruler is about 30 centimeters. To reach a single kilometer, you'd need more than 3,000 rulers. To reach 1 million kilometers, you'd need over 3 billion. Now multiply that million kilometers by about 9,460. That's roughly the number of times you'd have to stack 1 million kilometers to equal 1 light year. You could also try it with the Earth-Sun distance as a unit. The average distance between Earth and the Sun is about 150 million kilometers, known as an astronomical unit, AU. 1 light year is about 63,000 astronomical units. In other words, you could line up the Earth-Sun distance 63,000 times to equal 1 light year. That might be the cleanest way to visualize it, because at least the Earth-Sun distance has some grip on the imagination. You've seen diagrams of it. You know the Sun is far, but not impossibly far. Now stretch that distance tens of thousands of times. That's the scale astronomers deal with when they talk about distances between stars. And even those distances are tiny compared to galactic or intergalactic ones. But back to the unit itself. A light year is sometimes confused with light speed, as if it's a measure of velocity. This confusion pops up often enough that scientists sometimes use parsecs, another distance unit, to avoid the issue. But for general audiences, light years are far easier to work with than parsecs because the definition is intuitive once you break it down. It's just the distance light travels in a year. The challenge isn't the definition, it's the human mind trying to wrap itself around the distance implied by that definition. There's also an interesting secondary effect. When you start measuring things in light years, distances that sound huge suddenly sound small depending on the context. 4 light years feels enormous compared to anything in the solar system, but it's absolutely tiny on the scale of the galaxy. 100,000 light years feels massive until you compare it to the distances between galaxy clusters. Cosmic structure keeps outgrowing the units used to measure it, which is partly why cosmologists eventually abandon light years for other concepts entirely, like redshift. But we'll get to that later. For now, focus on the essence of the unit. It's tied to the nature of light, and light is the closest thing we have to a universal messenger. It moves fast enough to be useful, constant enough to build physics on, and limited enough to define the boundaries of what can be known at any given moment. A light year, therefore, is less a clever invention and more a measurement carved out by the structure of reality itself. But from a storytelling standpoint, the best way to internalize a light year is to think of it as the minimum unit where stars become neighbors instead of specks. Once you reach a scale where a year of light travel feels like a short hop, you're thinking in astronomical terms, and that's when the cosmos stops being a series of isolated objects and starts becoming a connected landscape shaped by the motion of light across vast distances. Next, we'll take this definition and use it to build a kind of intuition by stepping through what light travels in a second, a minute, an hour, a day, and finally a year, because that process shows exactly where our sense of scale breaks. If you try to picture a full light year in one leap, your mind has nothing to work with. It's like trying to imagine the size of a mountain while standing 2 inches from the rock face. There's no context, no perspective. That's why the best way to understand a light year isn't to attack the whole number at once, but to walk toward it step by step, starting with a light second and climbing the scale until your intuition finally gives out. That breaking point tells you something important about where human understanding stops being instinctive and starts being purely conceptual. Let's begin with something almost everyone has experienced: watching the moon. When you look at the moon, you're seeing it as it was just over a second ago. That short delay is the time it takes for light to cross roughly 384,000 kilometers, the average Earth-Moon distance. That's about 1.3 light seconds. This is one of the rare cases where a cosmic unit actually overlaps with a familiar sight. You might not feel the distance, but you've spent your life looking at something a little more than a light second away. This is a good anchor because a second is a small chunk of time you can feel. Counting one Mississippi maps pretty well onto the time it takes light to cross the gap between us and the moon. Already the scale is huge. If you tried to walk a single light second, you'd die of old age thousands of times before finishing. If you tried to drive it, you'd burn through every tank of gas you could ever imagine. Even Earth's fastest spacecraft take days to cover that distance. And for light, it's just a blink. A light minute expands things by a neat factor of 60. It's about 18 million kilometers. That number doesn't intuitively connect to anything, so picture something simpler. The Earth-Sun distance divided into slices. The Sun is about 8 light minutes away. You can use that to form a pretty clear mental picture. The sunlight warming your skin was emitted 8 minutes earlier. If the Sun snapped out of existence, hypothetically, you would keep orbiting a ghost for 8 minutes before anything changed. It's a strange thought, but one that helps you pin meaning to the unit. A light minute is the scale of our inner solar system. And here's the interesting part. 1 light minute is already farther than most spacecraft ever travel in months. Voyager 1, the farthest human-made object from Earth, moves fast enough to cross roughly a light hour in about a week, yet the numbers are still tiny compared to what light can do in that same time. A light hour is 60 light minutes, and at that scale, we're talking about more than 1 billion kilometers. 1 billion. Again, that word is so large that it tends to collapse into a mental category labeled big, but it's worth pausing on what it means. Imagine you could lay 1 billion rulers end to end, each one 30 centimeters long. Even if you stacked them around Earth dozens of times, you wouldn't come close to 1 billion. And that's the distance light tears through in just 1 hour. An ordinary highway drive doesn't even register as motion on this scale. A jet doesn't either. They're all effectively stationary compared to light. Once you stretch from a light hour to a light day, something breaks. A day is 24 hours, and multiplying 1 billion kilometers by 24 launches you into a realm where even the vocabulary feels insufficient. A light day is about 26 billion kilometers, far enough for light to pass the orbit of Neptune and keep going. Think about how often you've heard the phrase outer edge of the solar system. In normal language, it means very far. In light travel terms, that entire span is covered in 1 day. You might think you can still picture this because you've seen diagrams of the solar system. But those diagrams fool you, not because they're inaccurate, but because they're squeezed to fit the page. The real distances between planets are mostly empty voids bigger than anything you can visualize. A light day shows you that emptiness with brutal clarity. It's a measurement so large that the whole planetary system shrinks to a notch on a ruler. Now take that ruler and stretch it for a month of light travel. A light month is around 780 billion kilometers. close to the average size of the Oort cloud's inner boundary, the icy shell of material surrounding the Sun. When astronomers talk about comets coming from the far edge of the solar system, this is what they mean. Distances so vast that we rarely even talk about them without switching to light months or fractions of a light year. Light crosses that span in roughly 30 days. A spacecraft built with today's technology would need thousands of years. This is the point where human intuition usually collapses. A month of light travel is so far outside practical experience that it barely registers as a distance. You can imagine a month of time because your life contains plenty of them. But a month of continuous travel at 300,000 kilometers per second? There's no foothold for your imagination. The scale is too large, and the emptiness between objects gives your mind nothing to grip. So when astronomers talk about a full light year, 12 months of uninterrupted motion at the fastest possible speed, they're describing a distance that sits at the edge of what numbers can convey. A light year is simply 12 light months stacked together, and each light month is already a number so large that the leftover digits might as well be symbolic. Trying to imagine a light year from scratch feels like trying to imagine the number of grains of sand on a beach by staring at a single grain. The individual piece is manageable. The total overwhelms. But there's a trick to building intuition that actually works. Instead of trying to picture the entire distance at once, track where light would be at each step. You already know where a light second lands. It's near the moon. A light minute lands near the scale of planetary orbits. A light hour sails through the outer planets. A light day leaps past the solar system. A light month reaches the domain of comets. A light year pulls you away from the Sun entirely, into interstellar space. Once you map each step to something physical, you can start to feel the pattern. Every jump multiplies what came before. And unlike kilometers or miles, these units grow large quickly because the base unit, the speed of light, is so absurdly large to begin with. To appreciate why this matters, picture a timeline of light leaving the Sun. At time 0, the photons burst free from the Sun's surface. After 1 second, they're farther than the Moon. After 8 minutes, they're at Earth. After 5 hours, they're past Pluto's orbit. After a day, they're moving through the scattered debris beyond Neptune. After a week, they're deep into the outer reaches of the Kuiper Belt. After months, they're passing through regions where comets orbit. After a year, they've reached the realm where the Sun looks like any other star. This progression is what the term light year really encodes. It's not the number itself that matters, but the journey implied by that number. A light year is the boundary where stars begin to treat each other as neighbors rather than distant lights in the sky. It's the smallest meaningful chunk of interstellar distance. But to see how far beyond intuition this is, consider how long it would take a spacecraft to travel even 1 light second. Our fastest probes move at around 17 kilometers per second. That's incredibly fast by everyday standards, but compared to light, it's glacial. At that speed, it would take a spacecraft about 6 hours to cross a light second. And that's just the Moon's distance. For a light minute, you're looking at more than 2 weeks. For a light hour, months. For a light day, years. For a light year, tens of thousands of years. This mismatch, light crossing a distance in seconds that takes us years, is another clue to why the unit feels so abstract. We're used to measuring distance by travel time. Walk to the store, 10 minutes. Drive to the next town, 30 minutes. Fly across the ocean, several hours. We rely on travel time because it's something our senses can track. Our experience attaches meaning to movement. But with a light year, human experience is cut out of the equation. You can't stand in one place and watch something travel a light year. You can't make the distance more relatable by imagining yourself covering it. Human speeds are too small by comparison. Light years grow from motion we cannot participate in. This is why stepping through the smaller units is so important. Each step lets your intuition stretch just a bit farther before it snaps. You accept a light second because you can still link it to a familiar distance. You accept a light minute because you've heard the Earth-Sun figure before. You accept a light hour because you know planets are spread out. You accept a light day because you have some sense of the solar system's size. But by the time you reach a light year, you're so far beyond anything experiential that the unit becomes a mathematical construct. That's not a failure of imagination, it's the nature of the universe. The cosmos operates on scales where familiar intuition simply isn't built to apply. A light year is the smallest of these scales where the mind fully loses its grip, But the beauty of this approach is that it doesn't ask you to imagine the entire distance. It asks you to track growth, how quickly the scale expands as you increase the time. And when you feel that growth speeding up, you begin to understand why astronomers lean so heavily on the light year as a tool. It isn't because the unit is intuitive, it's because anything smaller would drown the numbers in zeros and anything larger would erase the differences between star systems. One more perspective helps solidify this. If the distance between Earth and the Sun were scaled down to 1 meter, then 1 light year would be roughly 63,000 meters. That's 63 kilometers. A long walk, a short car ride. But notice what's happening. By shrinking the solar system to something your mind can hold, you've also shrunk the light year to something manageable. This works only because both distances shrink together. If you kept Earth and the Sun at their real size, 150 million kilometers, and tried to imagine 63,000 of those stacked end to end, your intuition would collapse again. This demonstrates a key point. You can build intuition for ratios, not absolute values. The light year is useful because it preserves ratios. Stars measured in light years maintain their relative spacing in a way the mind can compare. You can imagine one star twice as far as another, even if you can't imagine the actual distances involved. That's the whole secret. We don't understand a light year by feeling it. We understand it by climbing toward it, second, minute, hour, day, month, year, and noticing when our intuitive sense stops keeping up. That threshold is where the cosmos begins. Before we even think about other stars, galaxies, or anything involving hundreds or thousands of light years, there's a much more immediate place where our intuition completely falls apart, our own solar system. It looks manageable in the diagrams: 8 planets, a few dwarf planets, some rings, some moons, all arranged neatly around the Sun like beads on a wire. But that diagram is a cheat. It has to be. If anyone drew the solar system to scale, you'd never fit it on a page, a wall, or a football field. The planets would all be microscopic dots, separated by vast oceans of blank space. And that blank space is what makes the distances so impossible to grasp. Even before you get to the first planet, things are already weird. The Sun itself sets the tone. Its diameter is about 1.4 million kilometers. That's a number so large that it's hard to internalize. If Earth were the size of a standard globe, the Sun would be roughly the size of a small room. And that's just the central object. Everything else we talk about in the solar system orbits around this massive sphere. But you don't feel the Sun's size when you look at it. You see a disk that looks small in the sky because it's 150 million kilometers away. That distance, called an astronomical unit, AU, is our first real taste of just how unhelpful our visual intuition is. You don't perceive 150 million kilometers when you step outside. You simply see daylight. Yet that distance is staggering. If you could somehow travel around Earth's equator non-stop in a jet, it would take you roughly 2 days. But the distance from Earth to the Sun is the equivalent of circling the Earth more than 3,700 times in a row. That mental stretch alone is enough to show that even the easy distances in space aren't actually easy. Now look at Mercury. It orbits the Sun at roughly 0.39 astronomical units, about 58 million kilometers. Tiny planet close to the Sun seems like it should feel compact. But 58 million kilometers isn't compact. It's nearly 150 times the distance from Earth to the Moon. If Earth had a single moon-sized object 58 million kilometers away, we wouldn't call that object part of our local neighborhood. We'd call it extremely distant. And that's the first gap in our intuition. We imagine the inner solar system as modestly sized because Mercury, Venus, Earth, and Mars look close together on charts. But in real distances, these worlds are separated by gulfs that would swallow anything human-made many thousands of times over. Venus, our nearest planetary neighbor, orbits at about 108 million kilometers from the Sun. Earth sits at 150 million. Mars is farther at roughly 228 million. If you stretch these numbers onto a straight line, the spacing between them would feel almost random because the orbital layout wasn't designed for neatness. It's a result of how the protoplanetary disk formed billions of years ago. And when you look at the system's spacing this way, you start seeing how deceptive the familiar diagrams are. Those diagrams condense tens of millions of kilometers into centimeters. Without meaning to, they distort your sense of distance by a factor of billions. One way to cure that distortion is to imagine shrinking the Sun to something familiar, let's say the size of a large beach ball, about 70 centimeters across. If the Sun were that small, Earth would be the size of a pea. Venus would be a slightly smaller pea. Mars would be a tiny grain, and Mercury would be barely bigger than a pinhead. This sounds cute and manageable until you look at the distances. The Earth pea would orbit the beach ball at about 75 meters away. That's nearly the length of a soccer field. Mercury's pinhead would be a third of that distance. Venus's pea would be more than halfway to Earth. Mars would be twice as far out as Earth. And that's still only the inner solar system. 4 small objects stretched across an area so large that you'd have to jog from one to the next. And here's the kicker. Between all those small objects is almost nothing, just vacuum. The planets don't form a chain. They're isolated specks separated by distances that the human body and human experience never evolved to imagine. Now move outward past Mars and you run into another psychological wall, the asteroid belt. Popular culture has filled people's heads with the idea that it's some kind of dense rock field where ships weave dramatically between tumbling boulders. But the truth is the exact opposite. The asteroid belt is almost entirely empty space. If you stood on one asteroid, you likely wouldn't be able to see another one with your naked eye. They're too far apart, hundreds of thousands, sometimes millions of kilometers apart. A spacecraft flying through the asteroid belt wouldn't dodge anything. It would pass through a void and occasionally pick up faint gravitational signatures of distant rocks. That's how empty the solar system is, even in the dense parts. Keep going outward and Jupiter finally appears at 5.2 astronomical units, 5 times farther from the Sun than Earth. That translates to about 780 million kilometers. By this point, the planets aren't just spread out. They're separated by distances that dwarf even the entire inner solar system. At this scale, Jupiter is like a massive buoy floating far out in an empty sea. Saturn orbits even farther at around 9.5 astronomical units. Uranus at 19 astronomical units. Neptune at 30 astronomical units. Each of these jumps multiplies the gap between objects until the solar system stops behaving like a system in the everyday sense. It becomes an archipelago with enormous stretches of void between islands. The outer solar system is where intuition completely surrenders. Neptune's orbit is so far out that sunlight is barely more than a faint glow compared to what we experience on Earth. Yet, when you look at diagrams, Neptune sits on the same page as Earth and the Sun, making it seem reachable, almost domestic. Reality couldn't be more different. Neptune is so far away that spacecraft launched at enormous speeds still take over a decade to reach the region near it, and that's following precisely optimized trajectories. The numbers only grow more absurd when you examine the objects beyond Neptune. Pluto orbits at about 39 astronomical units on average, but its path is elongated, sometimes dipping closer to Neptune and sometimes stretching even farther out. Beyond Pluto lies the Kuiper Belt, a ring of icy objects that stretches from roughly 30 to 50 astronomical units. This zone is populated with dwarf planets and countless smaller bodies, but once again they're scattered through immense space. You could place 1 billion Kuiper Belt objects randomly across the region and still have so much emptiness between them that calling it a belt feels like a poetic exaggeration. But even the Kuiper Belt is still only the outskirts of the solar system. Much farther out, thousands of astronomical units away, lies the Oort cloud, a vast spherical region filled with icy remnants from the solar system's earliest days. The Oort cloud might extend to 100,000 astronomical units or more. That's more than 1,000 times farther than Neptune. If the Sun to Earth distance were 1 step, the Oort cloud would be kilometers away. It's so distant that even the fastest spacecraft humanity has launched would need tens of thousands of years to reach it. And yet this unbelievable bubble of icy debris is still considered part of the Sun's gravitational influence. It's technically still our neighborhood. Here's where the solar system breaks human intuition completely. Even light, moving at the fastest speed allowed by the laws of physics, takes more than a year to reach the outer edge of the Oort cloud. Part of the solar system is literally more than 1 light year away. We tend to think of a light year as the distance between stars, and often it is, but the solar system's gravitational boundary leaks into that scale. The Sun's influence stretches beyond what our minds are comfortable with, because gravity weakens slowly and emptiness doesn't give you visual clues. This emptiness creates another problem for intuition. There's no sense of between. On Earth, if you travel far enough, you pass landmarks, trees, cities, coastlines. They let you gauge progress. In space, you can travel for millions of kilometers and see nothing but blackness and a slightly shifting star field. No feedback, no scenery change, nothing that says you're getting closer. Without visual cues, your mind collapses the distance into nothing. You might think of space travel like sailing across an ocean, but that metaphor fails because oceans have waves, wind, clouds, and curvature. Space has none of that. The scale is so vast and the void so featureless that your brain gets no footholds to understand how far you've gone or how far you have left. This is why even planetary missions involve years of travel. Not because the spacecraft move slowly, they're incredibly fast, but because the distances are enormous, beyond anything humans evolved to comprehend. A spacecraft traveling to Mars might launch with a speed so high that it could cross the United States in under a minute. Yet compared to the size of the solar system, that speed is trivial. The problem worsens when we try to imagine the orbits themselves. Planets look like they're following precise, elegant loops around the sun, but those loops are enormous and almost entirely empty. Earth's orbit alone is about 940 million kilometers long. That's nearly 1 billion kilometers just to make one lap. And we do one lap every year. If you stretched Earth's orbital path into a straight line, you'd have a track so long that you could place all the inner planets end to end millions of times before filling it. Even the concept of closeness loses meaning in the solar system. Earth and Venus can be the closest pair of planets for long stretches of time, but that closeness still means tens of millions of kilometers. Earth and Mars can be on opposite sides of the Sun, separated by over 400 million kilometers, then swing toward each other years later. When people talk about launch windows, they're not talking about convenient timing. They're talking about the geometry of two worlds moving through huge orbits in an enormous system. This is why building intuition for the solar system is so difficult. Our brains are wired to understand environments where the distances between things are small compared to the things themselves. In the solar system, the opposite is true. The spaces between objects are overwhelmingly larger than the objects. You could replace every planet with a grain of sand and keep the distances between them scaled up, and you'd still walk for minutes or hours before reaching the next one. The objects do not define the system. The emptiness does. And that emptiness sets the stage for understanding just how broken our intuition becomes when we move beyond the solar system. If the distances between planets, a handful of tiny worlds orbiting one star, already reach hundreds of millions or billions of kilometers, then the distances between stars aren't just bigger. They belong to a different mental universe entirely. The solar system is deceptively simple. It's orderly, predictable, and mapped with incredible precision. But when you strip away the diagrams, shrink the objects, stretch the distances, and imagine yourself drifting through that void, you begin to feel the real scale. An expanse so large that even light takes hours, days, or months to move across it. That's the solar system before we factor in a single star-to-star distance. And that's why, when we talk about light years, we have to start here, by showing that even our own celestial backyard is already far beyond the reach of natural human intuition. If the solar system already pushed your intuition to its limit, the moment you step beyond it, that limit isn't just broken, it disappears completely. Everything you thought was far inside the solar system becomes tiny compared to the distance to even the nearest star. And unlike the planets, which at least orbit in the same general plane, stars don't form neat patterns we can follow. They're scattered through three-dimensional space like glowing dust floating in an invisible ocean. We live inside that ocean, but we only ever see it projected flat onto the night sky. That flat projection fools us into thinking the stars are arranged like points on a dome. In reality, every one of those points sits at its own enormous distance, and no two of them are even remotely close to each other. Let's start with the star that sits closest to us, Proxima Centauri. It's part of a triple star system called Alpha Centauri, but Proxima sits slightly closer to us than its brighter siblings. The number you hear most often is about 4.24 light years away. That figure is small when you say it quickly. It sounds like 4 of something, just 4. But light years hide the scale. A single light year is nearly 10 trillion kilometers. Multiply that by a little over 4, and you get a number that doesn't fit inside normal intuition. Instead of thinking about trillions of kilometers, let's rethink the problem in a way that doesn't rely on numbers. Take the beach ball sun model again, the one where Earth is a P roughly 75 meters away. On that scale, where would Proxima Centauri sit? If the sun were in the center of a large park, Proxima wouldn't be at the edge of the park. It wouldn't be in the next neighborhood. It wouldn't even be in the next city. That star would be more than 20,000 kilometers away, roughly half the circumference of Earth. In other words, if our miniature sun sat in Paris, miniature Proxima Centauri would sit somewhere near Sydney. That's how far apart stars really are, even when they're neighbors. Most people picture stars as dotted fairly close together because constellations look like tight patterns. But if you could teleport instantly to the region around Proxima Centauri and look back, the sun wouldn't look like a bright, dominant object. It would appear as a modest star among many, barely noticeable, and you'd have to know exactly where to look to even pick it out. The space between stars is so large that even the combined brightness of billions of them can't fill it. That's because we're not talking about large distances compared to planets. We're talking about distances compared to entire solar systems. To make sense of how extreme this is, consider how long it takes light to travel those 4+ light years. Light is the fastest thing nature allows. It takes 8 minutes to get from the sun to Earth. It takes a bit more than 4 hours to reach Neptune. It takes about half a day to leave the solar system entirely, and then it takes over 4 years to get to the next star. Light, which crosses millions of kilometers in seconds, spends the vast majority of its interstellar journey moving through emptiness so enormous that those millions might as well be inches. Now imagine making that trip with actual spacecraft. This is where star-scale distances become truly unreal. The fastest spacecraft humanity has launched, the Parker Solar Probe, moves at speeds that would make a fighter jet look like it's standing still. At its top speed, near the sun, it travels fast enough to circle Earth in under 15 minutes. But even at that speed, reaching Proxima Centauri would take tens of thousands of years. By the time such a spacecraft arrived, human civilization would have transformed many times over. Languages would have shifted, cultures would have changed, and the people who launched it would be as distant from the arrival as the Stone Age is from us. Another way to appreciate the scale is to look at our best attempts to leave the solar system. Voyager 1, launched in 1977, is currently traveling through interstellar space by the technical definition, meaning it has crossed the heliopause, the region where the solar wind gives way to the galactic environment. But calling it in interstellar space can be misleading. Yes, Voyager has left the sun's bubble, but it hasn't even taken a meaningful step toward Proxima Centauri. In nearly 5 decades of travel, it has covered about 1/20,000th of the distance to the nearest star. Even if it kept going without slowing down, which it won't, it wouldn't reach Proxima for another 75,000 years. That is what nearest means on the scale of stars. Even light-year numbers don't tell the full story because they hide how much emptiness exists between stars. Inside the solar system, the emptiness feels like the main story. Between the planets, there's a vast void, but in between stars, the void grows so much that the solar system feels dense by comparison. Imagine scattering a few grains of sand across an entire continent. That's closer to how star density works. The Milky Way contains hundreds of billions of stars, but the galaxy is so big that they're extremely spread out. Our sun is in a pretty typical neighborhood, neither star-rich nor star-poor. Yet the distance to Proxima is still 4 years of light travel away. Because stars are so far apart, the idea of traveling between them quickly becomes science fiction. We talk about interstellar travel the way we talk about fantasy kingdoms. Interesting to imagine, but completely beyond our physical reach right now. But even imagining it highlights the problem. If we built a spacecraft that could travel at 10% the speed of light, 1,000 times faster than anything we've ever launched, Proxima would still be a 40-year journey. And that's assuming perfect engineering, 0 breakdowns, no radiation problems, no fuel constraints, and a level of technology we haven't come close to achieving. Those 40 years also don't include acceleration and deceleration. The real trip could take a human lifetime. This is why astronomers constantly emphasize that stars are not like cities you can travel between with better vehicles. Stars are like islands, separated by oceans, so vast that even the fastest currents take generations to cross. And unlike oceans where you can replenish supplies or stop along the way, space offers no checkpoints. No fuel stations. No emergency islands. Just emptiness extending in every direction. Another challenge is that the galaxy itself is moving. Stars orbit the center of the Milky Way at different speeds. They drift relative to one another over time, so Proxima isn't even fixed at that current distance. It moves. Our Sun moves. In tens of thousands of years, Proxima won't be our closest neighbor anymore. Another star will drift into the nearest position, not because it's coming toward us intentionally, but because everything in the galaxy is in slow, constant motion. That motion happens so gradually that it means nothing on human timescales, but on cosmic timescales, neighborhoods evolve naturally. This brings up a point that often surprises people. Stars are not evenly spaced. Some regions are denser, some are emptier. In parts of the galaxy closer to the core, stars sit much closer together, sometimes less than a light year apart. In parts farther out, especially in the halo, stars can be separated by enormous gaps. We live in a middle zone where spacing is moderate by galactic standards. Moderate, in this context, still means more than 40 trillion kilometers to the closest star. Let's push the intuition further by thinking about the star field as a whole. From Earth, you might look up at constellations and assume the stars in those patterns sit near one another. But constellations are illusions. The stars in Orion, for example, range from around 25 light-years away to more than 1,000. They only appear grouped because we see them from a particular viewpoint. If you could float above the galaxy and look at star positions from another angle, Orion would scatter like dropped beads rolling across a table. No recognizable pattern at all. This point matters because it highlights the main issue with imagining interstellar distance. Our senses were never meant for three-dimensional cosmic structure. When you step outside and look at the sky, you don't see depth. You see brightness, you see projection. That projection hides the true spacing and gives you no clues about how far away anything is. A bright star might be close, or it might be incredibly distant but luminous enough to appear close. A dim star might be near but small, or far but faint. Without physical measurement, you'd never know. That's why astronomers had to spend centuries developing ways to measure stellar distances. The most intuitive method is parallax, watching how a star's apparent position shifts as Earth moves around the Sun. But even that method runs into trouble fast. The closer stars show measurable parallax, but most stars are so far away that their parallax shifts are smaller than the width of a human hair, viewed from kilometers away. Space agencies need incredibly precise instruments, like the Gaia mission, to detect those minuscule shifts. The fact that we need billion-pixel telescopes and extreme precision just to detect tiny wiggles in star positions is another clue about the insane distances involved. One of the wildest realizations about the nearest stars is that their spacing determines how isolated we really are. If stars were only a few billion kilometers apart, let's say the distance from the Sun to Neptune, space travel would look completely different. We could imagine building infrastructure between worlds. Radio signals would arrive quickly. Travel time would feel long but achievable, but the actual spacing means that even communicating with another civilization near Proxima would involve 8 years of waiting for a round-trip signal at light speed. For actual travel, you're talking timescales as long as civilizations themselves. This is why astronomers don't casually say the nearest star is only 4 light-years away. As if that's close. It's not. It's unimaginably remote. We use the word nearest only because everything else is even farther. Another way to grasp interstellar distance is to think about how long stars live. Our Sun will shine for billions of years. But if you launched a spaceship today and it somehow kept moving toward Proxima Centauri indefinitely, it might actually arrive long before the Sun finishes its life cycle. That's how big the numbers are. They're large on the scale of stars' lifespans, not just human lifespans. You could launch a ship at the dawn of early human civilization and it still wouldn't be close to arriving today. Our species hasn't been around long enough to match the travel time. And there's an even stranger twist. Proxima Centauri isn't a typical destination star anyway. It's a red dwarf, dim, small, and active. It blasts flares thousands of times more powerful than anything our Sun produces. Any planet in its habitable zone sits so close that these flares would regularly bathe it in radiation. Even if we could get there, it's not a relaxing place to live. The nearest true Sun-like star is Alpha Centauri A, which is farther away. So even our best-case scenario for nearest star is complicated. All of this leads to the same conclusion. The distance between stars isn't a scaled-up version of the distance between planets. It belongs to a different category. Once you leave the solar system, the universe stops being a structure you can imagine in familiar terms. It becomes something so spread out that even light struggles to connect one part to another. People often ask, why don't we just go to the nearest star? It's only 4 light years away. But only is doing a lot of work in that sentence. 4 light years is the distance that exposes the limits of human intuition more than anything else in astronomy. It reveals that our sense of space, shaped entirely by life on a small planet, is not remotely equipped to handle the reality beyond our solar system. The moment you understand that, you start to appreciate just how extreme the gulf between stars truly is. We live inside a vast city of stars, the Milky Way galaxy. When we talk about the Milky Way, most people might picture a dense, bright swath of stars, maybe something like a cosmic cluster. But what the Milky Way really is, a gigantic flattened disk of stars, dust, and gas, so spread out that it's hard for our minds to grasp its enormity. Here's how the numbers sketch it out. The Milky Way's disk is roughly 100,000 light-years across. It contains somewhere between 100 and 400 billion stars, most of them scattered through that disk. The disk is relatively thin compared to its width. Most of it is only about 1,000 light-years thick, though the central region is thicker and more complex. Our own home, the solar system, sits about 27,000 to 30,000 light-years from the galactic center, roughly a third of the way out from the center to the edge. What that means for neighborhood. When you grow up thinking about the sky as a dome overhead, it's easy to assume that stars are tightly packed, or at least within a manageable neighborhood. But scaled properly, the Milky Way is far more like a thin, sprawling pancake than a dense ball. Billions but spread thin. With hundreds of billions of stars spread across a 100,000 light-year disk, average star-to-star distances are enormous. Even in regions with many stars, close might still mean hundreds or thousands of light-years. The night sky illusion. From Earth, because we're inside the disk and view it edge-on, the densest part appears as a bright band. That band creates the impression of closeness, when in reality, those stars are hugely distant. Clusters and pockets. The Milky Way isn't uniform. More stars cluster toward the central bulge and spiral arms. Other zones are sparse. That unevenness makes some regions feel denser, others almost empty. Why our brains fail on galactic scale. The same cognitive breakdown described earlier, with light years, planets, and interstellar gaps, happens again on galactic scales. Only this time it's even worse. No landmarks. There's no street sign, no fixed point for comparison. The next star system may be thousands of light years away, with nothing in between. Empty vastness masked by faint light. The Milky Way looks like a continuous glow only because of the collective light from countless stars. But between those stars lies near total emptiness. Space so vast that even light takes years to cross. Numbers lose meaning. Saying 100,000 light years across sounds big. But without an intuitive reference, it remains abstract. Our minds can't picture something so big. It simply becomes huge without real structure. What it reveals about our place in the galaxy. Understanding the Milky Way as a broad, thin disk full of sparsely distributed stars reshapes how we see our place in the universe. Isolation by default. Even though there are billions of stars around us, the vast distances mean we're effectively alone, at least in any human-scale sense of close. Galactic scale motion. Everything in the Milky Way orbits the center, including us. The Sun, with our solar system, completes one full revolution around the galactic center roughly every 250 million years. Galactic home is emptier than it feels. The sky looks full of stars, but the majority of the space between stars is empty. That emptiness shapes how we think about travel, communication, and cosmic scale. Understanding the Milky Way like this helps explain why cosmic distances, even just star-to-star distances, can feel so ungraspable. We're not living in a galaxy packed with stars like a swarm of bees. We're living in a galactic neighborhood that's sprawling, thin, and mostly empty, with stars scattered like distant streetlights across an immense, dark plain. If the last chapter made the Milky Way feel huge, crossing it will make the scale feel almost comical. A galaxy isn't just big, it's so far beyond anything our species has ever dealt with, that even imagining the trip exposes the limits of human intuition. We tend to think of long journeys as things that take hours, days, or years. Even the idea of a spacecraft taking a decade to reach the outer planets feels long. But once you shift from traveling within the solar system to traveling across the galaxy, you move from human timescales to geological and even civilizational timescales. The numbers stretch so far that your brain stops knowing what to do with them. Let's start simple. The Milky Way is about 100,000 light-years across. If you could travel at the speed of light, which you can't because physics blocks that, you'd still need a full 100,000 years to cross it from one end to the other. That's longer than the entire history of human civilization. Agriculture started roughly 10,000 years ago. Written language is maybe 5,000 years old. The pyramids are roughly 4,500 years old. Every single kingdom, empire, religion, technology, cultural shift, and scientific discovery in the entire timeline of humanity fits inside one tiny slice of that travel time. Light would need 10 civilizational lifetimes to reach the other side. Now, imagine using something slower than light, which for us isn't imagination, it's reality. Every spacecraft we've ever launched is so slow compared to light that the comparison barely makes sense. Even if we built something thousands of times faster than today's probes, something not just futuristic, but borderline theoretical, the journey across the Milky Way would still take so long that whatever launched the ship might not even exist when it arrived. Languages change in centuries. Civilizations rise and fall in millennia. But traveling the galaxy takes tens or hundreds of thousands of millennia. It doesn't happen in generations. It happens in epochs. This is why the idea of crossing the galaxy sounds adventurous in science fiction, but breaks apart the moment you attach real physics to it. In fiction, characters cover thousands of light years in an afternoon because the story needs them to. But in reality, the scale is so huge that distance stops being something you travel and becomes something you only describe. The galaxy might as well be an ocean the size of a continent. You can cross a lake with a rowboat. You can't cross an ocean with a rowboat, and crossing a continent with an ocean is simply impossible. The mind-bending part is that even though the galaxy is enormous, it's not empty of structure. It's full of star systems, clusters, nebulae, star-forming regions, and spiral arms, all arranged in a pattern shaped by gravity, motion, and billions of years of evolution. But to us, it doesn't feel like a structure we can navigate. The scales are too big to visualize. If you zoomed out far enough to see the Milky Way as a whole, the solar system would disappear. Zoom in to where the solar system becomes visible, and the rest of the galaxy vanishes into abstractions. Humans can't see the entire structure and the local details at the same time. You either understand the big picture or the close-up, but not both at once. Not with intuition alone. Consider the sun's own path through the galaxy. Our solar system isn't stationary. It orbits the galactic center at roughly 220 kilometers per second. That speed sounds fast, and it is. At that velocity, you could travel from New York to Los Angeles in about 20 seconds. But even at this ridiculous speed, the Sun needs about 250 million years to complete a single orbit around the Milky Way. That means the dinosaurs experienced only about 2 galactic years before the asteroid hit. Homo sapiens have existed for a fraction of 1% of a galactic year. Every time you move through daily life, the solar system is actually hurtling through the galaxy at incredible speed. Yet the galaxy is so vast, you never notice. Motion on that scale becomes invisible. That scale also hides incredible variety. The Milky Way isn't just a disk, it has spiral arms, curved lanes of higher star density that sweep around the center. Our solar system sits in a smaller feature called the Orion Arm, sandwiched between two larger ones. These arms are not structures you could visit the way you might drive to another region on Earth. They are enormous stretches of stars and gas, thousands of light years wide. Moving from one arm to another involves distances so large that, again, Even light takes centuries just to cross part of the gap. Traveling across the galaxy isn't just about distance, it's also about motion relative to everything else. Stars move, clouds of gas drift, stellar clusters migrate, spiral arms slowly rotate. Over millions of years, stars drift into new neighborhoods. That's why looking at the sky today doesn't tell you what the galaxy looked like in the past or will look like in the future. If you time traveled 100 million years forward, the constellations would be unrecognizable. Every star would have moved to a new position. The patterns that seem fixed and eternal to us are temporary ripples in a constantly shifting system. This motion complicates any attempt to imagine crossing the galaxy because you're not traveling through a static structure. You're trying to move across something that behaves more like a slow, drifting crowd. A star several thousand light years away won't be in the same place by the time a spacecraft reaches its direction. Planning an interstellar trip across that much space would require predictions so long-term and detailed that even small errors in the starting conditions could send the calculation off by entire light years. And yet, despite its size, the Milky Way isn't the biggest galaxy. It's reasonably large, but not extreme. There are galaxies hundreds of thousands of light years across. Some giant ellipticals stretch 1 million light years or more. By those standards, the Milky Way is middle of the road. But the fact that something so large is only average tells you everything you need to know about how unprepared our brains are for galactic scale. We evolved to navigate terrain measured in meters, not cosmic structures measured in light years. Another angle that helps reveal the magnitude of the Milky Way is to think about communication rather than travel. Even if no one ever tried to physically cross the galaxy, communication itself collapses at these distances. Imagine a message sent from one end of the Milky Way to the other. If it travels at light speed, the fastest speed possible, it still takes around 100,000 years to arrive. Whoever receives it won't just be a different generation. They'll be part of an entirely different era. Civilizations could rise and disappear between the sending and receiving of a single message. If the sender wanted to know whether it was received, that confirmation would take another 100,000 years to return. A full round trip, send, receive, reply, would be 200,000 years. That's older than modern humans. This fact alone explains why, even if intelligent life is common in the galaxy, it might feel silent. The distances are so large that communication is effectively impossible. A civilization could be thriving a few thousand light years from here, sending signals in every direction, and we wouldn't know. Their messages wouldn't reach us for millennia, and anything we send wouldn't reach them until long after our species changes in ways we can't predict. The silence of the galaxy may not be real silence. It may just be the reality of light speed limitation on a scale too large for meaningful exchange. Now, think about what happens to a star system as it orbits the galactic center. The Sun has completed about 18 or 19 orbits since it formed roughly 4.6 billion years ago. That means the solar system has lived through multiple passages through different parts of the galaxy. Denser regions, sparser regions, perhaps even nearby encounters with star clusters long gone from our neighborhood. Earth's environment is shaped not only by local factors like the Sun and planets, but also by the solar system's long, slow journey through the Milky Way's gravitational landscape. Over tens of millions of years, that environment changes because the galaxy itself is not uniform. If you tried to cross the galaxy intentionally, you would essentially be riding that enormous gravitational structure the way a leaf rides a current. But unlike a river, the galaxy's current doesn't take you somewhere quickly. It takes you around the center slowly, predictably, and relentlessly. It's a motion so vast that you never feel it, yet so important that it shapes the entire cosmic environment around us. Another point that helps anchor the scale: the thickness of the galactic disk is tiny compared to its width. Most of the stars, including our Sun, live in a slice only a few hundred to 1,000 light years thick, depending on the region. This creates a structure that is much more like a cosmic sheet than a sphere. If you view the galaxy from above, it looks enormous. But if you view it edge-on, the disk becomes a narrow line with a bulge in the middle. It's difficult to picture something so immense in two directions and yet so relatively thin in the third. That mismatch itself adds to the difficulty of grasping the true distances involved. Even the simple act of saying our galaxy is 100,000 light years wide hides complexity. The The boundary of a galaxy isn't a hard edge. It trails off. Stars blend into the halo. Dark matter extends far beyond what our instruments can easily detect. The actual size depends on how you define the edge. Some definitions place the diameter closer to 150,000 light-years. Others go higher. The structure is so enormous and diffuse that even defining it pushes the limits of measurement. But regardless of where the edge sits, the takeaway is the same. Crossing the Milky Way is beyond any speed or technology we can imagine with current physics. The distances erase the concept of travel. They erase the concept of communication. They erase any expectation that two distant civilizations might interact meaningfully. Even light, the fastest thing in the universe, moves too slowly on galactic scales. This is the moment in the story of cosmic distance where your brain finally runs out of familiar analogies. Up to now, you might have managed to stretch your intuition a little by thinking in terms of road trips, flights, months, years, or centuries. But the galaxy outscales all of that. A road trip analogy doesn't work. A flight analogy doesn't work. Even the entire span of human history isn't long enough to relate to these distances. Once you reach galactic scale, the numbers break your intuition completely. Crossing the Milky Way forces you to accept a strange truth. The universe is not built for human travel, not at this scale. It's not even built for human imagination. It's built for stars, gravity, and time on billion-year scales. And those ingredients create structures so enormous that even light struggles to map them. When people picture the center of the Milky Way, they often imagine some kind of glowing hub, something bright, maybe chaotic, maybe full of energy. And that's not entirely wrong, but the real galactic center is stranger and more extreme than anything the human mind naturally expects. It's a region so different from our local neighborhood that it might as well be a different kind of universe. The rules haven't changed, but the conditions have, and when conditions push physics to its limits, our intuition usually collapses. The first thing to know is that the galactic center is crowded in a way that doesn't translate well to everyday experience. Not city crowded, not stadium crowded. We're talking star density that's millions of times higher than the region where the sun lives. In our part of the galaxy, stars are spaced so far apart that if the sun were the size of a pea, the next closest star would be another pea sitting dozens of kilometers away. But near the center, stars are so densely packed that they're separated by distances small enough that gravity between them is constantly noticeable. Everything there is interacting with everything else. Nothing sits quietly. But the crowding is only the beginning. The real anchor of the galactic center is something we can't see directly. A supermassive black hole called Sagittarius A star. It's about 4 million times the mass of the Sun. That's not hyperbole. It really is 4 million solar masses squeezed into a region so small that if you replace the Sun with this black hole, the entire inner solar system would be inside its event horizon. And this monster sits right at the heart of the Milky Way, shaping the motion of entire clusters of stars. Even though the black hole itself is invisible, its presence is obvious because the stars around it move in ways that nothing else can explain. Some of them whip around the center at thousands of kilometers per second. That's fast enough to cross the width of Earth in a few seconds. These aren't slow, stately orbits like planets around the sun. They're tight, fast, dramatic loops governed by intense gravity. One star in particular, known informally as S2, completes an orbit roughly every 16 years. That means it swings close, slingshots around the black hole, and flies back out again at ridiculous speeds. Watching these stars move was how astronomers confirmed that Sagittarius A star really is a black hole. Nothing else in the universe bends motion that sharply. The environment around that black hole isn't just crowded and fast, it's turbulent. Clouds of gas swirl under tidal forces. Radiation blasts from hot material collapsing inward. Shockwaves ripple through regions where stars form, die, and collide on timescales that feel short compared to the quiet pace of life in our part of the galaxy. If you could teleport into that region, which you wouldn't survive, you'd see a sky glowing with far more stars than ours, each brighter and more energetic, and a background saturated in radio emissions, X-rays and infrared light from matter under extreme stress. The strangest thing is that all of this is invisible from Earth in normal light. Dust between us and the center blocks the entire view. If you point an optical telescope toward the galactic center, you see almost nothing. It's only when astronomers use radio waves, infrared wavelengths, and X-ray detectors that the structure comes into focus. Suddenly the hidden scene appears: dense clusters, swirling gas, radiation storms, and the gravitational choreography of stars whipping around something they cannot touch. Even though Sagittarius A/E is enormous compared to any star, it's tiny compared to the scale of the Milky Way. 4 million solar masses is a lot, but the entire galaxy contains hundreds of billions of stars, so the black hole is only a fraction of a percent of the galaxy's total mass. Yet because it sits at the center, it acts like a weight that everything else orbits around, directly or indirectly. Think of it less like a cosmic drain and more like the anchor of a spinning wheel. Without it, the inner regions of the galaxy would drift and scatter. With it, the structure stays coherent for billions of years. Now, here's the part that really breaks intuition. Even though the center is violent and active, it's not the most extreme black hole out there. It's actually one of the calmer, supermassive black holes known. Some galaxies have black holes billions of times the mass of the Sun. Compared to those monsters, Sagittarius A star is modest. But for us, being this close to such an object is still extraordinary. We're about 27,000 light-years away, comfortably distant but still part of a galaxy whose entire structure is influenced by that central gravitational anchor. Another surprising detail is that the galactic center is not static. It changes slowly over long periods of time, but in cosmic terms, slowly still means dramatic. Stars fall inward. Gas clouds drift too close and get shredded. Sometimes the black hole flares when material accumulates or collapses into it. These flares don't threaten us, but they're reminders that the center is alive in a way our region of the galaxy is not. It breathes energy. It rearranges itself. It constantly reshapes the environment in ways we only observe through indirect signals. When we talk about the center of the Milky Way, we're also talking about a snapshot of something that looked different in the past and will look different in the future. Millions of years ago, the center was probably brighter and more active. Millions of years from now, it may flare again or settle into a quieter pattern. The dynamics are long-term but powerful. And while Earth never gets close enough to experience those changes directly, the broader gravitational dance affects the whole disk over geological timescales. Another thing people often misunderstand is the shape of the central region. It's not just a single bright core, there's a bulge of stars that swells out of the disk, creating a kind of three-dimensional structure at the heart of the galaxy. This bulge contains older stars, clusters, and complicated gravitational patterns that don't resemble the flat, orderly rotation of the outer disk. The bulge is messy, it's thick, it's dense, and right inside it is the even denser, faster, hotter region around the black hole. Trying to imagine this environment from a human perspective is almost impossible. If you lived near the galactic center, the night sky would be dozens or hundreds of times brighter because of the number of nearby stars. Space travel would be more dangerous because of radiation and gravitational interactions. Planet formation would be influenced by density and turbulence. Entire solar systems might be disrupted over millions of years by passing stars. It's not the kind of place where a quiet, stable planetary system like ours would easily survive for billions of years. This is part of why our location in the galaxy matters. We live in a calm part of the disk, far from the center. There are still hazards: supernova, gamma-ray bursts, passing molecular clouds, but nothing like the chaos near Sagittarius A star. If the solar system had formed closer to the center, Earth's history would have been completely different, assuming the planet could have formed at all. Too much radiation and gravitational interference would make long-term stability unlikely. Life, if it appeared, would struggle to persist on billion-year timescales. So the galactic center isn't just a place that's hard to imagine, it's a place that shapes the rest of the galaxy through its mass, its energy output, and its long-term influence on stellar motion. It's the heart of the Milky Way, even if the heart beats slowly on cosmic timescales. The most startling part is that everything happening there, every flare, every collapse, every star orbit, is happening right now. We just see it with a delay. The galactic center is 27,000 light-years away, so the light reaching us today left during the last ice age. When we observe the center today, we're seeing ancient activity. Anything happening today, meaning literally today, won't be visible to us until 27,000 years from now. This time, delay applies to every object in the galaxy. The farther out you look, the older the light becomes. Even inside our own galaxy, you're looking into history, not the present. And that's where distances really start to bend the mind. The center feels distant, but in galactic terms, it's close. Other galaxies are millions of light years away. Clusters of galaxies are hundreds of millions of light years away. The cosmic web stretches across billions of light years. The distance to the center of the Milky Way, the place with a 4 million solar mass black hole tearing space apart, barely registers on that scale. This chapter matters because it marks the point where we shift from distances between stars to distances that shape entire galaxies. Understanding the galactic center gives you a foothold for the next leap, stepping outside the Milky Way entirely. Once you move beyond our galaxy, cosmic distance enters territory so vast that even calling them light years strains meaning. The region we can see, because light had time to travel from there to us, is called the observable universe. It doesn't mark the limit of existence, but the edge of what's within our visual and instrumental reach. The observable universe has a radius of about 46 billion light years, meaning the furthest things we can detect now are approximately 46 billion light years away in proper distance. That gives a diameter of roughly 93 billion light years across. That number is far bigger than one might naively expect, given the universe's age of about 13.8 billion years. It seems paradoxical. How can we see 46 billion light years when the universe is only 13.8 billion years old? The answer lies in the fact that space itself expands. When light from a distant galaxy began its journey, that galaxy was much closer. But as light traveled, space stretched, carrying the source farther away. By the time we detect the light, the source now sits at a dramatically larger distance than when the light left it. Thus, the light travel time, roughly 13.8 billion years, doesn't equal the present distance. The expanding space transforms that travel into an effective present separation much larger than the light year count alone suggests. Inside that 93 billion light year sphere lie hundreds of billions, likely trillions of galaxies, each with its own stars, planets, and possible wonders. Yet even this huge observable universe may be only a tiny fraction of the entire cosmos. The universe beyond the observable region could be far larger, maybe infinitely large, but we have no way to see or test it. That means every time you look at a deep field image from a telescope, all those tiny galaxies, you're seeing history. That light has traveled billions of years across expanding space before reaching your eyes or sensors. On smaller scales, planets, stars, even galaxies, we can at least approximate distance with mental models. On cosmic scales, there are no familiar anchors, just empty space, expanding invisibly. Thinking in light years becomes almost meaningless. 46 billion is a number so detached from daily experience that it's not big. It's abstract. Trying to imagine traveling or even conceptualizing that distance feels futile. Even light itself takes billions of years, and space along the way expands under its own rules. Our galaxy is just one among potentially trillions across the observable universe. The observable universe itself is enormous, but even that might be just a small patch of a far grander or infinite reality. The scale is so vast that distance, as we normally understand it, loses almost all intuitive power. If you think of cosmic distance as a ladder, from planets to stars to galaxies, the observable universe is the top rung humanity has ever reached. Beyond that, it's dark, unknown, maybe infinite. When you go beyond nearby stars or nearby galaxies, using light years becomes problematic. That's why astronomers often switch to cosmological redshift, denoted Z, or directly work with look-back time, our redshift distance, instead. Here's why, and what it really means. Space is expanding. When we observe a distant galaxy, the light we receive has traveled across space that has stretched during the journey. That means the current distance to that galaxy is usually much larger than the distance light traveled. Expressing that separation in light years becomes ambiguous. Do we mean how far light traveled, or how far apart they are now? For very distant objects, those two numbers differ significantly, sometimes by tens of billions of years of travel. Also, the universe's expansion isn't uniform in naive terms. Different parts expand, sometimes accelerating. Using fixed distance units fails to capture that dynamic. Because of this, distance as of today and distance when the light left become two different things, and light-year matches neither cleanly unless you specify which. That's messy. Redshift is measured by the stretching of light's wavelength. As space expands, light waves get stretched, shifting towards longer, redder wavelengths. The more stretching, the larger the shift, and the higher the redshift value Z. By measuring redshift, astronomers infer not only how long ago the light was emitted, eyes look back time, but also how much the universe has expanded since then, giving a handle on the object's present-day distance under a cosmological model. For very distant galaxies, those seen near the edge of what's visible, redshift is more meaningful than raw distance. That's because the stretching of space dominates any intuition of distance traveled. In short, light-year measures how far light traveled. Redshift captures how much the universe stretched during that travel, and lets us infer how far things are now. Scientists observe a distant galaxy's light and split it into a spectrum, recording characteristic fingerprints, elements, emission or absorption lines. They compare those lines' wavelengths with their known rest values. If the light has been stretched, the lines move to longer wavelengths, towards red or infrared. The amount of shift gives the redshift Z. From Z, using cosmological models, they compute approximate look-back time when the light was emitted, and co-moving distance, rough estimate of current separation, accounting for expansion. For example, a distant galaxy with high redshift may have emitted its light 12 billion years ago, but by the time we see it, the universe expanded so much that the galaxy might be many tens of billions of light-years away. It ties together space and time. Because of expansion, observing distant objects is like looking back in time. Redshift encodes that history. It avoids misleading intuitions. Saying this galaxy is 20 billion light-years away suggests a simple point A, point B travel, which space doesn't obey at cosmic scale. It scales. We use redshift from relatively nearby galaxies up to the farthest observable galaxies, enabling a consistent framework across vast time and distance. Galaxy is flying away like a rocket. Not quite. The galaxies aren't necessarily moving through space at super-fast speeds. The space itself expands, carrying galaxies apart. We see the galaxy as it is now. No, we see it as it was when the light left, often billions of years ago. The redshift indicates that then versus now difference. Light-year distance equals travel time. For nearby stars, that works. For distant galaxies with expansion, it doesn't. That's why light-year becomes less useful far out. Switching from light-years to redshift is more than a technicality. It reflects a shift from thinking of space as static to thinking of the universe as dynamic, stretching, evolving, growing. It shows that distance isn't fixed. The nearness or farness of an object changes over cosmic time. In a way, redshift is our cosmic measuring tape, not one that stays fixed, but one that flexes as the universe grows. It lets astronomers map where things were, where they are now, and how space itself changed in between. Once you start thinking in redshift instead of light years, you've stepped into a version of the universe where distances behave in ways that don't resemble anything in normal life. Up close, space seems simple. You measure from point A to point B, and that's that. But on cosmic scales, billions of years, billions of light years, that idea stops working. Space itself refuses to stay fixed. It stretches, it changes shape, and it does it everywhere at once. You don't feel it happening, but the evidence is built into the light from every distant galaxy. The idea of expansion is easy to say and surprisingly difficult to picture accurately. Most people imagine galaxies flying outward from a central point, like shrapnel from an explosion. But that's not really how it works. There's no center, there's no edge, and the galaxies aren't racing through space like projectiles. Instead, the space between galaxies expands. If you've heard the raisin bread analogy, it's actually not bad. In dough rising in every direction, each raisin gets farther from every other raisin as the dough expands. But even that analogy has a catch. Raisin bread expands in a larger space, and the universe doesn't expand into anything. There's no outside, the expansion is internal. It's the distance between things growing, not things moving toward an exterior. What makes this hard is that our minds are built for fixed stages, rooms, landscapes, Surfaces, where motion happens inside the stage. In the universe, the stage itself changes size. It's like watching a play where the theatre doubles in size every few minutes while the actors stay roughly where they were. You can try to imagine that, but your intuition fights back. That's what cosmic scale does to the idea of distance. If you want to understand how astronomers deal with this, you have to follow how they describe the universe's expansion in terms of scale. Cosmologists use something called the scale factor, a number that tracks the size of the universe at different times. Think of the universe today as having a scale factor of 1. At earlier times, the scale factor was smaller. For example, when the universe was half its current size, the scale factor was 0.5. When it was a tenth the size, the scale factor was 0.1. Redshift is directly tied to that scaling. It tells you by how much space has stretched since the light you're seeing was emitted. Here's where things get strange. When you look at a galaxy with a high redshift, you're not just seeing a distant object. You're seeing an ancient object that emitted its light when the universe was dramatically smaller, sometimes just a few % of its current size. Because expansion happened while the light was still traveling, the object is now much farther away than the light travel time suggests. That's why astronomers talk about look-back time instead of raw distance. The universe is a moving target. You can't talk about how far something is without specifying whether you mean then or now. To get a feel for this, imagine a galaxy whose light has taken 10 billion years to reach us. You might think, okay, so it's 10 billion light years away. But the actual distance now is much larger because space expanded during those 10 billion years. The galaxy might currently be 25 or 30 billion light years away, depending on how the expansion accelerated during that time. That gap between the travel time and the present distance grows bigger the farther out you look. At the edge of the observable universe, the light travel time is 13.8 billion years, but the present distance is about 46 billion light years. The difference is so large that the travel time becomes the less useful number. This is one of the reasons astronomers sometimes switch between different types of distances. Look-back time tells you how long the light traveled. Comoving distance tells you the present separation. Angular diameter distance and luminosity distance help translate between size and brightness in an expanding universe. These terms sound technical, but the reason they exist is simple. Distance has multiple meanings when the stage is stretching. No single measurement captures the whole picture. Another counterintuitive part is that expansion affects all of space. It's not stronger in one area than another. A common misunderstanding is that galaxies push space outward. They don't. Expansion happens even between regions with nothing in them. It's not a force, it's a property of space-time. If you somehow removed every galaxy from the universe, space would still expand. Matter affects the rate of expansion, but not the existence of expansion itself. This is where dark energy enters the story. You don't need to dive into deep theory to grasp the basic idea. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. In the late 1990s, astronomers discovered that distant supernovae were dimmer than expected. That meant they were farther away than the standard model predicted. Something was making the expansion speed up. The simplest explanation, and still the leading one, is that empty space has an energy built into it. As the universe grows, more empty space appears, and with it more of this energy. That energy acts against gravity, pushing galaxies farther apart at an ever-increasing rate. This accelerating expansion deepens the weirdness of cosmic distance. It means that portions of the universe we can see today will eventually slip beyond the horizon. Not because they move away too fast, but because the space between us expands so quickly that even light can't cross the gap. A galaxy that's visible now may eventually become unobservable. It won't vanish, but there will come a time when any light it emits can never reach us. The expansion carries it out of causal contact. In a few trillion years, distant galaxies will fade into invisibility one by one until only the local group remains visible. The rest of the universe will drift beyond reach. This future fading isn't immediate, but it shapes how astronomers think about the universe today. The observable universe isn't a static bubble. It's a region defined by what light has had time to reach us within the age of the universe. As expansion continues, the boundary evolves. What lies beyond that horizon isn't necessarily gone, so it's just unreachable. The stage expands faster than the speed at which information can travel. That brings us to one of the biggest misconceptions in all of cosmology: the idea that nothing can go faster than the speed of light. That's strictly true when you're talking about objects moving through space. But the expansion of space itself can create effective separations faster than light without violating relativity. Galaxies at great distances recede from us faster than the speed of light. Not because they're moving that fast, but because the expanding stage stretches the distance between us. Light emitted from them now will never reach us. That isn't breaking physics. It's following the rules of a dynamic universe. What makes this fascinating and difficult is that you have to juggle different kinds of motion. There's peculiar velocity, which is the motion of objects through space, and there's recessional velocity, which is the movement caused by space expanding. Peculiar velocity might be a few hundred kilometers per second for a galaxy. Recessional velocity can be tens of thousands of kilometers per second, or even exceed the speed of light at great distances. The two motions combine to create a cosmic flow that looks nothing like motion in a fixed space. Here's a real example to help ground this. The Andromeda galaxy is moving toward us through space, getting closer and causing its light to be slightly blue-shifted. That's peculiar velocity. But most galaxies are redshifted because they're carried away by the expansion of space. And at large distances, expansion wins completely. Peculiar velocity becomes irrelevant. It's like trying to swim against a current that gradually accelerates. Near the shore, you can fight it. Farther out, the current becomes too strong to resist. Beyond a certain point, no matter how much effort you make, you're getting swept outward. Another layer of complexity comes from the fact that the universe wasn't always expanding at the same rate. Early on, expansion was slowing down because matter's gravity was pulling everything inward. Only after billions of years did dark energy dominate and turn the slowdown into a speed up. That shift means the relationship between redshift and time isn't linear. When you see a galaxy at redshift 1, the universe was about half its current size. At redshift 2, it was much smaller again. At redshift 7 or 10, the domain of the earliest detected galaxies, the cosmos was a tiny fraction of its present scale. This evolution means every deep field image from a big telescope is simultaneously a map of distance, a map of time, and a map of expansion history. The faintest galaxies aren't just far away. They belong to an era when stars were forming differently, when the chemistry of the universe was simpler, and when the structure of the cosmos was only beginning to take shape. That's why interpreting these images is more than just listing distances. You're looking into a past that lives under different cosmic rules. One of the hardest things to accept is that the universe has no outside perspective, where you can view the whole structure at once. The expansion is everywhere. There's no external vantage point where you could watch the universe expand like a balloon inflating. Every observer, no matter where they're located, sees everything else moving away. If you teleport to a distant galaxy, you won't find yourself at the edge of some explosion. You'll see galaxies receding from you in all directions as well. That's not an illusion, it's a natural consequence of expansion happening uniformly. This is where the concept of the cosmic horizon becomes crucial. The horizon marks the limit beyond which light has not had enough time to reach us since the beginning of the universe. It's similar to standing in a fog. You see a boundary not because anything special happens there, but because light from beyond that boundary can't reach your eyes. The observable universe is just the region where the particles that emitted the light are close enough, not in distance but in time, for their radiation to arrive. And because expansion stretches everything, that boundary doesn't line up neatly with any single number. It's part time, part distance, part scale factor, all wrapped together. All of this leads to a bigger point. When astronomers stop using light years for distant objects, they're not being picky. They're dealing with a universe where distance is a moving target. A galaxy that's billions of light years away isn't sitting at a fixed coordinate waiting for us to measure it. The space between us and that galaxy is stretching, and the stretching defines what distance even means. This shift in thinking is tough at first, but freeing. Once you stop trying to compare cosmic distances to everyday experiences, things start to click. You stop picturing galaxies in fixed positions and start imagining them as part of a dynamic fabric. You stop thinking of space as a static room and start thinking of it as something alive, evolving, and always in motion. And that mindset lets you understand the universe on its own terms, not on the limited terms of everyday intuition. When people hear the phrase observable universe, they usually picture a giant sphere around us, as if we're sitting at the center of everything. That sounds egocentric at first, but the reason has nothing to do with our location in the universe. It has everything to do with light, time, and the fact that information travels at a finite speed. We don't see the universe as it is now. We see the universe as it was, limited by how far light has been able to travel since the beginning of time. That simple constraint shapes what we can and can't detect, and it's the reason our visible universe forms a bubble around us. The starting point is straightforward. The universe is about 13.8 billion years old. That means the farthest anything could have sent us light is 13.8 billion light years. But that gives you the wrong impression because space expanded during those 13.8 billion years. The objects whose light is just now arriving are not 13.8 billion light years away today. They're roughly 46 billion light years away because the space between us grew as the light traveled. This is why the observable universe's radius is far larger than the simple age of universe number would suggest. It's like watching waves move across an ocean that's expanding under them. What makes this tricky is that the observable universe isn't a physical shell. There isn't a barrier out there. There's just a limit to what light has had time to reach us. You can think of the boundary like the edge of a flashlight beam in fog. The fog doesn't end there, but beyond that point, the light is too scattered to reach you. In the universe's case, the fog is the beginning of time. Anything beyond the observable boundary isn't invisible because of distance alone. It's invisible because its light hasn't had enough time to get here. This means every observer anywhere in the universe sees themselves at the center of their own observable bubble. If you hopped across the universe and asked any galaxy what it sees, the answer would be similar. A sphere around itself, filled with galaxies and structured in a familiar way. That's a consequence of expansion and the fact that light spreads out in all directions. No matter where you stand, you're always at the center of what you personally can see. This is one of the most unintuitive aspects of cosmology, and it's something people push back on when they first hear it. They imagine the universe having a literal center, and they imagine us sitting in that spot. But the observable universe is not the universe. It's simply the part we can see from here, given the amount of time light has had to reach us. The real universe could be far larger. It could be infinite. It could have structure we can't detect. We have no direct way to know yet. We only know what light has delivered. To understand how this bubble forms, it helps to follow light back to the earliest moments of the universe. Immediately after the Big Bang, the universe was hot, dense, and opaque. Photons bounced around like light inside a thick fog. They couldn't travel freely because they kept scattering off electrons. Only after the universe had expanded and cooled enough for atoms to form, roughly 380,000 years after the Big Bang, did space become transparent. That moment is called recombination, and it produced the oldest light we can see today, the cosmic microwave background, or CMB. This light fills the universe and washes over Earth constantly, but because the universe expanded and stretched it, we see it now as microwave radiation instead of visible light. The CMB acts like a wall, not because anything physical is there, but because it marks the earliest possible light we can receive. You can't see past the moment the universe turned transparent. Anything before that is hidden behind a curtain of plasma. That means the edge of the observable universe is not only determined by distance and expansion, but also by eras of transparency. We see the universe at a younger and younger age as we look farther out, but once we hit the CMB, the picture stops. Beyond that, we rely on models, not direct light. This time layering is one of the strangest consequences of living in an expanding universe. When you look deeper into space, you're not seeing farther into a landscape. You're seeing farther back in time. The edge of the observable universe corresponds to a moment, not a place. It's less like standing on a mountain and looking out at distant peaks, and more like scrolling back through the timeline of the universe until you reach the earliest chapter recorded in light. Closer in, the light we see comes from galaxies that matured over billions of years. Farther out, we see younger galaxies forming their first stars. Push even deeper, and you find objects that existed when the universe was only a few 100 million years old. The light from those objects is stretched by expansion. making them dimmer and redder. Eventually, as you approach the limit, you find that deep infrared glow of the CMB, the relic of the early universe. That progression gives astronomers a built-in way to trace cosmic history without traveling anywhere. The universe brings its past to us. Because of this stretching, the observable universe is slowly changing. Over time, more distant regions become visible as their light reaches us for the first time. At the same time, because expansion is accelerating, some regions that are visible today will eventually move beyond our future horizon. In trillions of years, only a fraction of what we see now will still be observable. It's a strange dual motion. The past becomes visible slowly, while the future slips away. One of the misconceptions people have when discussing the observable universe is that objects near the boundary are physically at the edge of something. They're not. The galaxies emitting today's CMB photons aren't special galaxies. They're just ordinary galaxies that happen to be at the right distance to send light that's arriving at this moment. If you wait another 1,000 years, the edge shifts outward very slightly, and you'll see light from a region that's currently just outside the visible limit. The boundary is temporal, not spatial. Another subtle point is that the observable universe isn't a perfect sphere in practice, even if we describe it as one. The expansion is uniform on large scales, but the universe has structure. Galaxies cluster. Superclusters form long filaments. Dark matter shifts the path of light through gravitational lensing. All those effects warp the way light reaches us. The large-scale shape averages out to a sphere, but the details are more like a three-dimensional quilt stitched together from billions of individual light paths, each one bent and delayed by intervening matter. That bending is what allows us to see features that would otherwise be too faint or too far. When a massive galaxy cluster sits between us and a more distant galaxy, it can act like a lens and magnify the distant object, letting telescopes observe galaxies from early epochs that would normally be invisible. These gravitational lenses let astronomers effectively borrow mass to extend their reach. It's one of the reasons we've been able to detect galaxies from the first few 100 million years after the Big Bang. Without lensing, they'd be beyond our capability to detect. This layered, distorted, expanding view leads to a striking idea. The observable universe is different for every object inside it, and it changes over time. The universe you could observe if you waited 1 billion years would be bigger, but also emptier in the far distance as accelerated expansion drags galaxies beyond your horizon. If intelligent life evolves in a distant galaxy billions of years from now, their observable universe will be different from ours. They'll see their own bubble, centered on themselves, with regions we can see today long gone from their view. This is why the observable universe is not the universe. It's the universe as filtered by distance, time, expansion, and the speed of light. It's a slice of a much larger whole, possibly an infinite whole, and it's constantly changing as light continues to arrive. One of the most mind-stretching consequences of this idea is the notion that there are regions of space we will never interact with, even if humanity survives for unimaginable spans of time. We can't see them today because their light hasn't arrived. We won't see them in the future because expansion will push them away faster than their light can travel. They exist, but they're beyond all possible contact. They're part of the universe, but not part of our cosmic neighborhood. This creates a kind of natural limit to what any civilization can ever learn directly about the cosmos. That limit shapes the questions astronomers ask. They can model what lies beyond the observable universe, but they can't measure it directly. They can infer some properties from the uniformity of the CMB and the distribution of galaxies, but beyond that, the picture fades. It's not that the universe turns mysterious, it's that the laws of physics impose a boundary on our access to information. What's remarkable is that even with this limit, the observable universe still gives us a vast amount to work with. We can map galaxy clusters billions of light years away. We can trace the evolution of cosmic structure over most of the universe's lifetime. We can measure the chemical fingerprints of early stars. We can track how expansion has shifted over time. We can even detect ripples in space-time from merging black holes billions of light years away. The bubble we're trapped inside is large enough for entire lifetimes of discovery and large enough to reveal the broad history of the cosmos. And the bubble expands not because the universe changes, but because our access to its history deepens. Every year, light from regions slightly farther away arrives here for the first time. It's like reading a book where a new page appears every moment. Eventually, the book ends at the CMB, but the unfolding pages leading to it contain almost everything about how the universe grew from near uniformity to the richly structured place we see today. This is the essence of the observable universe, a moving boundary defined by time, not space. A visible sphere centered on every observer, not because we're special, but because light has limits. A record of the universe's past delivered to us by photons that have traveled across a stage that's stretched under them. And a reminder that even on the largest possible scale, what we see is only part of the whole. The moment you accept that the observable universe is only the part that light has delivered so far, another question pops up. What about the regions beyond it? If the universe is bigger than our visible bubble, maybe much bigger, Anne, could we ever reach those far zones given enough time, better technology, and patience? It feels like the answer should be yes. After all, if something exists, why wouldn't it be reachable? But when you bring expansion into the story, the idea of reachable becomes slippery. There are parts of the universe that we will never see, never visit, and never exchange information with, no matter how long we wait or how far we travel. They're not behind walls or hidden by matter. They're simply too far away in an expanding universe. To understand this, imagine the observable universe again, but shift the focus. Instead of asking, how far can light travel toward us? Flip the direction and ask, how far could light, or a spaceship, or any signal starting from here, travel outward? These two horizons aren't the same. The one we talked about earlier, the edge created by how long light has been traveling toward us, is the particle horizon. The one defined by how far anything we emit can get is the event horizon. And that event horizon is the more sobering one because it defines the true limit of future contact. The event horizon is shaped by the accelerating expansion caused by dark energy. As the universe expands faster and faster, distant regions are pulled away at increasing speeds. Space doesn't drag galaxies through a medium, it stretches the distance between them. At some distances, the stretching becomes so rapid that light emitted now will never make it far enough to reach us. Not because the light slows down, but because the space ahead expands too quickly for the light to close the gap. It's like walking toward a moving walkway that's accelerating away from you. Your steps don't slow, but the walkway's retreat wins. That edge, the distance beyond which communication becomes impossible, is the cosmic event horizon. It's the point of no return in cosmology. And unlike the particle horizon, which grows over time as more ancient light reaches us, the event horizon is more like a shrinking circle in terms of contact possibilities. Every billion years or so, more galaxies drift into the unreachable zone. They haven't vanished, and they aren't jumping away at incredible speeds. They're simply being carried by expansion into regions where even light, the fastest thing in existence, can't bridge the distance. This is the part that breaks intuition. We're used to the idea that if you start early enough and travel long enough, you can eventually get anywhere. On Earth, that's true. In the solar system, still true. Even for the Milky Way, if you imagine absurdly patient travelers and technologies far beyond what we've built, you could reach any star. But the universe doesn't follow that rule. Expansion creates a growing fraction of space that's permanently inaccessible. The more time passes, the bigger that fraction becomes. To get a better feel for this, it helps to picture two galaxies separated by a vast distance. They're not moving through space like cars on a highway. The space between them stretches. Each galaxy sees the other drifting away, but that drift is caused by expansion. Up to a certain point, the galaxy's own motion, its peculiar velocity, can counteract that drift. But at greater distances, the expansion wins. There is a separation scale beyond which, even if a galaxy fired its rockets at full throttle forever, it could never overcome the increasing gap. Light, the ultimate benchmark, can't do it either. This leads to an odd conclusion. The universe contains regions that are physically there, with their own galaxies, planets, and potentially civilizations, yet nothing they do can affect us, and nothing we do can affect them. They are as unreachable as the interior of a black hole is to the outside world. The barrier isn't physical, but the effect is the same. It's a limit baked into space-time itself. This might sound pessimistic, but understanding it changes how you think about cosmic history. Right now, when we look out into the universe, we see other galaxies, clusters, and superclusters. The large-scale web of cosmic structure stretches across tens of billions of light years. It's a vast, interconnected picture, but that picture is temporary. Far in the future, expansion will thin out the view. Most galaxies will gradually fade from visibility as their light becomes too redshifted to detect. Their signals will stretch into wavelengths so long that no telescope could pick them up. Eventually, only the galaxies bound to us by gravity, mainly the Milky Way and Andromeda, long since merged into one, will remain visible. Everything else will reside beyond the event horizon. That future universe will feel much smaller, not because the universe collapsed, but because everything else drifted out of view. Observers living in that far future will see an empty cosmos. They'll see no evidence that galaxies ever filled the sky. The cosmic microwave background will fade to the point of being nearly undetectable. To them, the universe will look static, silent, and local. Without relics like ancient records or preserved cosmological data, they might never deduce that the universe was once full of galaxies moving apart. They might conclude the universe is timeless and unchanging. For us, living in a relatively early era, we're in a privileged position. The universe is still visible on large scales. We can observe galaxies at all stages of evolution. We can detect the CMB with extraordinary precision. We can measure the expansion rate, map the distribution of dark matter, and study the early universe through the faintest galaxies Webb has picked up. If humanity had appeared trillions of years from now instead of today, almost all of that information would be inaccessible. The grand cosmic story would be invisible. The existence of an event horizon also reframes how we think about exploration. When people talk about interstellar or intergalactic travel, they often imagine expansion as a background detail, something that matters only on scales we'll never reach. But expansion does more than separate galaxies. It sets hard boundaries. Even if we mastered propulsion and built ships that could travel near the speed of light, our reach would still be finite. We could visit some galaxies if we launched early enough, but not most of them. And the window for reaching even the reachable ones keeps shrinking as the universe accelerates. This doesn't make exploration pointless. The local group of galaxies, the Milky Way, Andromeda, and a few dozen smaller galaxies, will remain gravitationally bound for the entire future of the universe. No amount of expansion will tear them apart. That's our long-term cosmic neighborhood. But the rest of the universe, that's slipping away right now. And that slow slipping is continuous. Do nothing for 1 trillion years, and the universe will look like an island of stars surrounded by darkness. One of the more mind-stretching consequences of an event horizon is what it implies about communication. You could send a signal toward a distant galaxy today, and that signal would travel outward normally. But beyond a certain distance, the space between sender and receiver expands too quickly. The signal gets stretched, slowed in terms of its arrival progress, and eventually overtaken by expansion. The receiver never gets it, even if they wait an infinite amount of time. It's not that the signal vanishes. It simply never catches up. That same rule applies in reverse. There are galaxies whose light we see today. Galaxies near the boundary of the observable universe. We see their ancient light because it left them billions of years ago when they were closer. But if those galaxies emit light now, that newer light will never reach us. We see their past, but not their present or future. We get a brief window into their history and then lose them forever. This creates a one-way relationship. We see them, but they will never see us. Not now, not later. Never. The light we're emitting today is headed toward a future that, for many regions, it will never reach. These unreachable zones aren't rare or exotic. They make up the majority of the universe. The part we can see is only a portion. The part we can influence is smaller still, and both regions change over time. All of this comes from one fact. Expansion accelerates. If expansion were steady or slowing, the story would be different. Light would always have a chance to bridge the gap, given enough time. But with acceleration, the gap grows faster than light can chase it. And because dark energy seems tied to the very fabric of space, this acceleration isn't expected to stop. The future universe will be dominated by this widening, this stretching, this retreat of the distant. Once you internalize this, another idea becomes apparent. The cosmic horizon defines the ultimate limit of what any physics experiment can discover. You can measure only the universe that can communicate with you. Everything beyond that is permanently cut off from observation. Even if you built detectors the size of galaxies or telescopes that used entire stars as lenses, the event horizon blocks all possible contact. This isn't a flaw in technology, it's part of the geometry of space-time. Here's a simple way to see the difference between reachable and unreachable zones. If you send a signal to a nearby galaxy next door in the local group, that galaxy will receive it eventually because gravity keeps that region together. Send a signal to a galaxy 10 billion light-years away, and physics says the signal might not catch it. Not because the galaxy is moving quickly, but because new space is forming between you and it faster than your signal can cross the old space. This leads to a final twist. Even though these horizons limit what we can see or reach, the universe itself may be infinite. We're constrained inside a finite bubble of awareness, inside potentially infinite space. Picture being inside a ship in the middle of an infinite ocean, but with a fixed limit on how far your vision can extend. The ocean might go on forever, but you'll always see only a circle around you. Expansion shrinks the practical size of that circle over time. What lies beyond your sight might be vast, but you'll never confirm it. Yet, even with all these limits, we have enough data from the observable universe to understand the big picture of cosmic evolution. We know the universe is expanding. We know it has a history. We know it has structure and temperature and motion. We know how stars formed, how galaxies grew, how elements built up. Our bubble contains enough history to reconstruct the story, but we will never see all of the chapters and we'll never meet the distant characters. Some of them are already beyond reach. Others will cross the horizon eventually, and in the very distant future, the universe will grow quiet as the faraway lights fade. If you've followed the last few chapters, you've probably noticed that cosmologists don't talk about distance the way anyone else does. They switch terms constantly: look-back time, co-moving distance, angular diameter distance, luminosity distance, and at first it feels like needless jargon. Why not just stick to light years? Why keep introducing more categories? The answer is that in an expanding universe, distance doesn't behave like a single, simple idea. No one number captures everything you care about. The moment you look beyond nearby galaxies, you have to decide which version of distance you actually mean. It helps to start with something familiar. On Earth, distance is straightforward. If you say two cities are 400 kilometers apart, that number tells you how long it might take to drive, how much fuel you'll use, and even roughly how the trip will feel. It's all the same idea. That collapses completely once you step into cosmology. In a dynamic universe, things that seem like they should match, how far away something looks, how long its light traveled, how far it is right now, no longer line up. You need different measurements because each one answers a different question. Let's start with the simplest of the cosmic distances. Look-back time. Look-back time is exactly what it sounds like. How long the light has been traveling before it reached us. If you observe a galaxy and the light left it 5 billion years ago, its look-back time is 5 billion years. This is great for building a timeline. It tells you what era of the universe you're looking at. But it doesn't tell you how far away the galaxy is today. That's because the universe expanded the entire time that light was in flight. A galaxy with a 5 billion year look-back time might be 8 or 10 billion light years away now. That's why look-back time is more of a when number than a how far number. Another important distance is co-moving distance. This one measures how far away something is right now, with the expansion factored out. Think of it as the distance you'd measure between two galaxies if you froze the expansion of the universe at this instant. It's like pausing a movie to see where the characters actually are. When astronomers want to build maps of large-scale structure, clusters, filaments, voids, they use co-moving distance. It describes the fixed layout of the cosmic web beneath the expansion. Co-moving distance also lets you compare where things were at early times to where they are today. Without it, the growth of space would confuse any attempt to talk about the structure of the universe in a consistent way. Two galaxies might have been close together billions of years ago, but expansion stretched the space between them. Their co-moving distance stays the same because the stretching is factored out. It's like converting old prices into modern dollars. You remove inflation so you can compare eras cleanly. Next up is proper distance. This one sounds like it should be the real distance. After all, it's called proper, but it's actually slippery. Proper distance is the instantaneous distance between two objects at a specific moment in cosmic time. Imagine freezing the universe at a particular second and pulling out a giant ruler. Whatever number you measure is the proper distance for that moment. That means proper distance changes with expansion. It grows as the universe grows. If you freeze the universe now, that's one proper distance. If you freeze it 1 billion years later, the proper distance is bigger. So proper distance is a good snapshot, but not a stable reference the way co-moving distance is. Then you get to distances that sound even stranger: angular diameter distance and luminosity distance. These exist because astronomers often don't know how far away something is directly. What they can measure is how bright it looks, or how big it appears on the sky. The problem is that in an expanding universe, apparent size and brightness don't follow the simple rules you'd expect. Angular diameter distance answers this question. If you know how big something really is, say a galaxy or a cluster, how far away must it be to appear the size you observe? In ordinary space, the farther something is, the smaller it looks. But in an expanding universe, this relationship breaks at large distances. Objects at extreme distances start to look larger than you'd expect. Not because they're close, but because they emitted their light when the universe was younger and smaller. The light traveled through evolving space. Angular diameter distance corrects for all of that, giving you the distance that matches its apparent size under cosmic expansion conditions. Luminosity distance solves a different problem. If an object is a known intrinsic brightness, a standard candle, how far away must it be to appear as faint as it does? Again, in static space, this is straightforward. Dimmer means farther, but expansion stretches the wavelength of light, reduces the energy of each photon, and spreads the photons over a larger surface area. All of that makes objects appear dimmer than they would in a non-expanding universe. Luminosity distance adjusts for this, giving a measure that matches observations. These distances aren't competing definitions. They're tools for answering different questions. If you want to know what the universe looked like at different times, you need look-back time. If you want to build a map of today's large-scale universe, you need co-moving distance. If you're studying how objects appear, how bright or how large, you need luminosity or angular diameter distances. They're all describing the same universe, just from different angles. All of this complexity comes from one simple fact: space isn't static. If the universe didn't expand, you wouldn't need any of these distinctions. Distance would mean one thing: the space between 2 points. Expansion breaks that unity. The stretching of space changes photon energy, apparent size, and travel time. It warps light paths. It alters relationships between brightness and distance. After a few billion years of stretching, the connection between how far and how things look becomes deeply nonlinear. This is why cosmology relies so heavily on redshift. Redshift isn't a distance itself, but it's the most direct, clean measurement we can make from distant objects. By measuring how much the wavelength of light has been stretched, astronomers get a handle on the scale of the universe at the time the light was emitted. With a good model for how the universe has expanded, they can translate that stretch into any of the other distances. Without redshift, cosmology would be blind. Redshift also cleans up a lot of confusion about travel time versus separation. If the redshift is high, that means the universe was much smaller when the light left the object. The actual present-day separation might be enormous because the universe kept expanding during transit. This is why distant galaxies can be receding faster than light. Not because they're speeding through space, but because the space between us and them is stretching. That stretching creates distances that can be larger than any light travel time implies. One of the most unintuitive consequences of these distance definitions is what happens to angular diameter distance at large redshift. Normally, you expect an object to look smaller the farther away it is. But in cosmology, beyond a certain redshift, around z, approximately 1.5, objects start looking larger again. Not dramatically larger, but enough that the relationship reverses. This happens because when the light left those galaxies, the universe was much smaller. The galaxies were physically closer to us in co-moving coordinates at the time of emission. As the universe expanded, the distance the light traveled increased, but the geometry of expansion bends the relationship between size and distance. This effect means that the most distant galaxies can actually look slightly larger in angular size than galaxies that are closer but still far away. It's counterintuitive, but it falls right out of the math of expansion. Luminosity distance has its own quirks. It grows faster than you'd expect because of redshift dimming and expansion. When the light's wavelength stretches, each photon carries less energy. When the universe expands while the light travels, the photons spread over a larger area by the time they reach us. Combined, these effects make distant objects appear dramatically fainter than distance alone would predict. Without correcting for these effects, you'd underestimate their distance by huge factors. This complexity is exactly why the 1990s discovery of cosmic acceleration was possible. By comparing redshift to luminosity distance for certain supernovae, astronomers noticed that the supernovae were dimmer than expected. That meant they were farther away than any steady expansion model allowed. The only explanation that fit the data cleanly was an accelerating expansion. If distance weren't tied to light stretching and apparent brightness in such non-linear ways, that discovery would have been much harder. Here's a way to visualize all these distances working together. Picture a galaxy so far away that its light took 12 billion years to reach us. The look-back time is 12 billion years. The co-moving distance today might be around 30 billion light-years. The proper distance at the moment the light left might have been 3 or 4 billion light-years. The luminosity distance, the distance that explains its faintness, might be even larger than the co-moving distance. The angular diameter distance, the distance that explains its angular size, might be much smaller. They're all describing different relationships between you, the galaxy, and the evolving space between you. Once you understand these distances, a lot of cosmology suddenly becomes clearer. The Hubble diagram, redshift versus luminosity distance, tracks expansion history. The cosmic web maps rely on co-moving distance. The study of early galaxy structure uses angular diameter distance. The interpretation of ancient light relies on look-back time. All these tools let astronomers turn the universe's expansion into something measurable rather than a giant blur of changing space. The key insight is this: no single distance captures the whole picture. You need the right tool for the right question because the universe is not a fixed stage. It's a growing, shifting arena where light doesn't travel through a static medium. It travels through a changing space-time that alters it along the way. The result isn't chaos, it's a set of different but consistent ways of describing one universe. If you've ever read about astronomy, you've seen distances given in light years so often that the unit starts to feel universal. It's simple, intuitive, and tied directly to the speed of light. 1 light year is the distance light travels in a year. You'd think that if any field needs clear, consistent units, it's cosmology. But on the larger scales, light years break down so completely that astronomers can't rely on them without heavy caveats. They're still useful for stars, nearby nebulae, and even close galaxies. But once you approach the deep universe, light years stop working as a clean measure of how far away something is. And the reason is the same one that has threaded through every chapter so far. The universe expands while the light is in transit. To understand why this ruins light years, it's worth revisiting what a light year assumes. It assumes that space itself isn't changing. If light travels for 1 year in a vacuum, it covers a fixed distance. Add 10 more years, you add 10 more light years. Everything is linear and predictable. That works great inside the Milky Way. It even works for talking about nearby galaxies like Andromeda. But the moment you cross into regions where expansion matters, anything beyond a few 100 million light years, this simple interpretation slips. The light that reaches us didn't travel through a static arena. It moved through space that stretched under its feet. The stretching increases the total distance the light had to cross, which means the number of light years it implies is no longer simply distance equals speed times time. The most obvious problem shows up when you look at extremely distant galaxies. Suppose a galaxy has a look-back time of 13 billion years. You might think it's therefore 13 billion light years away. But what that number really describes is the time the light spent en route, not the distance the galaxy is from us now. During the 13 billion years that light traveled, the universe expanded significantly. So the galaxy is much farther today, maybe 30 billion light years away in co-moving distance. If you try to describe this with light years directly, you run into the question, do you mean the light travel distance or the actual distance now? They're not the same, and the universe doesn't give you a single answer. This isn't just a semantic annoyance, it has real consequences. If you said casually that a galaxy is 30 billion light-years away, someone might assume that means the light took 30 billion years to reach us, which is impossible because the universe hasn't been around that long. But if you instead say the light took 13 billion years to reach us, someone else will assume the galaxy is 13 billion light-years away today, which is also wrong. Light-years simply don't carry enough information on their own for an expanding universe. Another issue appears when you try to describe the farthest observable light. The light we detect from the cosmic microwave background, the oldest light we can see, has been traveling for about 13.8 billion years. You could say the CMB has a look-back time of 13.8 billion years, but the region of space that emitted that light is now more than 45 billion light-years away in co-moving distance. Again, using light-years without qualifiers hides the deeper truth. Light-years don't map cleanly to distance when the underlying space is stretching. Even worse, some galaxies we can see today are already receding faster than light due to expansion. That doesn't violate relativity because nothing is moving through space faster than light. The space itself is expanding. But this creates another place where light years break intuition. If a galaxy is receding faster than light, you might think its photons should never reach us. But they do because when they were emitted, the expansion was slower and the photons could make progress inward before the acceleration ramped up. A static unit like the light year can't capture this story. It's a narrative tied to constant conditions, which the universe doesn't provide on large scales. Think about it this way. If you drive on a road that stays the same, you can measure distance by time. If you drive at 60 miles per hour for 2 hours, you've gone roughly 120 miles. Light years rely on the same logic, but imagine the road is stretching while you drive. Every minute, it grows longer. You could drive for hours and never reach the next town, not because you're slow, but because the road is being pulled apart. In that case, saying you traveled 120 miles in 2 hours doesn't describe the situation well. The distance you covered in terms of pavement relative to now is different from the distance you covered relative to when you started. That's exactly what happens with photons in an expanding universe. Light years try to describe a dynamic trip with a static ruler. For most of human history, this wasn't a problem. People didn't know the universe was expanding. For stars and most galaxies near us, expansion is tiny compared to gravitational binding and local motions. But once telescopes began detecting galaxies at high redshift, everything changed. Redshift revealed the degree of stretching the universe underwent while the light was in flight. A galaxy at redshift 1 has its light stretched to twice its original wavelength. That tells you that the universe doubled in size since the light left. Higher redshifts mean even more stretching. Light years don't tell you any of that. They hide the most important part of the story. Not the distance, but the evolution. There's also a practical issue. The deepest objects we can observe have light travel times approaching the age of the universe. If we tried to describe their distance with plain light years, our language would break. The light year number would always look suspiciously close to the age of the universe, even though the objects are far more distant in co-moving coordinates. A galaxy that emitted its light 13 billion years ago is not 13 billion light-years away today by any meaningful geometric measure. So astronomers avoid the phrase because it's misleading. This is why cosmologists lean heavily on redshift. Redshift doesn't pretend that space stayed still. It encodes the ratio between the size of the universe at emission and the size today. Once you know that ratio, you can calculate whichever distance you actually need. Look-back time if you care about when it happened, co-moving distance if you care about where the object is now, luminosity distance if you care about how dim it appears, angular diameter distance if you care about how big it looks, and so on. These distances behave differently because they measure different relationships between you, the object, and the changing universe. Light years don't distinguish these relationships. They just say, light traveled for this long, which is only part of the story. There's also the problem that light years imply a constant speed through a neutral background. In cosmology, photon travel is not simply 1 year, 1 light year. Photons lose energy due to redshift. Their wavelengths stretch. Their arrival rate changes. Their momentum shifts. All these effects come from expansion, and none are captured by the light year unit. Light years assume that light moves over a fixed metric. But in cosmology, the metric itself evolves. If the ruler changes shape while you measure with it, the measurement no longer reflects the full situation. This doesn't mean light years are useless. They're fine within the local group. You can say the Andromeda Galaxy is roughly 2.5 million light years away, and everything works, because over that distance, expansion is negligible compared to gravity. But if you keep using the unit for galaxies at redshift 5, 10, or beyond, you'll give the impression that these extreme distances work like terrestrial ones. They don't. The universe isn't just larger, it's actively changing underneath the measurement. There's another subtle reason light years fail at large scales. The concept hides the difference between when light left an object and where the object is now. Because light moves at a fixed speed, humans naturally tend to equate travel time with distance. In everyday life, this is fine. But in cosmology, it's deeply misleading. If you say an event happened 12 billion light years away, you might mistakenly think you're describing where the event is located in today's universe. You're not. You're describing a moment in the universe's past. The object that produced that light may now be tens of billions of light years away, or may not exist at all in its original form. This creates an illusion that faraway galaxies exist at the distances we assign to the look-back times. But the map we imagine in our heads, galaxies sitting in a giant sphere at fixed radii defined by travel time, is incorrect. What we're actually seeing is a time-layered shell, where deeper shells correspond to earlier eras of the universe. We're seeing history, not geometry. Light years blur these distinctions, making it seem as though we're observing objects spread out in space, when in fact, we're observing them spread out in time. That misunderstanding can cause all sorts of mental errors about how the universe is structured. Light years also lead to another misconception, the idea that all distances are symmetric. If we see a galaxy 10 billion light years away in the sense of look-back time, someone might assume that observers in that galaxy see the Milky Way as it was 10 billion years ago. In reality, this symmetry breaks once you introduce expansion. The distances evolve differently depending on which observer's frame you take and when you consider the measurement. Co-moving distance handles this consistency. Light years do not. Even more confusing, if you stick to light years, you end up in conversations where something can be 46 billion light years away, even though the light took only 13.8 billion years to reach us. This sounds like a paradox if you think light years are an absolute geometric measure, but once you account for expansion, the number makes sense. The true present-day distance is larger than the travel distance because space grew during the journey. Without terms like co-moving distance or proper distance, you're stuck with a unit that can't describe what's actually happening. There's another problem. Light years create false ceilings. People hear that the universe is 13.8 billion years old and assume nothing can be more than 13.8 billion light years away. That assumption holds only in a non-expanding universe. In the real one, the observable universe extends far beyond 13.8 billion light years in size. The present-day radius of the observable universe is over 45 billion light years. That fact alone breaks the light year mental model because it shows that travel time is not the same as separation. The universe had already stretched enormously by the time those photons arrived. All of this leads to a conclusion that seems strange at first. Light years are perfectly fine for talking about stars and nearby galaxies, but the moment you reach cosmological scales, you need to abandon them if you want to avoid misleading yourself. They're not wrong, just incomplete. They assume static space. Cosmology demands flexible measurements that track evolution, stretching, and geometry all at once. That's why astronomers lean on redshift, co-moving distance, look-back time, and the others. Those units reveal the structure of the universe. Light years hide it. Redshift is one of those ideas that seems simple until you try to pin down what it actually measures. You hear it described as light stretched by expansion, or a measure of distance, or a measure of time, or a measure of velocity. And depending on the context, all of those can be partly true while still missing the full picture. Redshift sits at the intersection of space, time, motion, and gravity. It encodes how the universe has changed while light was on its way to you. It can tell you something about how far away an object is, but only if you treat the number carefully. And the deeper you go into the universe, the less helpful the simple analogies become. You can start with the most basic version, the Doppler effect. You've heard this idea everywhere. If something moves away from you, the waves it emits, sound waves for example, get stretched. The pitch drops. If it moves toward you, the waves get squeezed and the pitch rises. Light behaves similarly. If a luminous object moves away, the light shifts to longer wavelengths, redshift. If it moves toward you, the wavelengths compress, blue shift. For nearby stars and galaxies, this simple Doppler picture works fine. Astronomers routinely measure the motion of stars orbiting within the Milky Way using Doppler shifts. They use it to detect exoplanets tugging on host stars. They use it to study gases swirling around black holes. But as soon as you apply this idea to galaxies billions of light years away, the Doppler analogy collapses. Those galaxies aren't receding through space because of momentum, the way a car drives down a road. They're receding because the space between us and them stretches. They are, in many cases, moving away at speeds no object could achieve through motion alone. Some appear to recede faster than light, which is allowed only because expansion affects space itself rather than the objects inside it. If you insist on treating that as a Doppler effect, you quickly end up with impossible numbers. So redshift cannot be interpreted purely as a velocity, even though at low values it mimics one. That's why astronomers switch languages depending on the scale. For nearby galaxies, you can get away with saying the higher the redshift, the faster it's moving away. But at cosmological distances, the same statement stops being physically accurate. Redshift describes the growth of the universe more than the motion of the galaxy. Once you let go of the idea that redshift means velocity, a deeper understanding becomes possible. Redshift measures how much the universe has expanded between the moment light was emitted and the moment you receive it. If the universe has doubled in size since the light left, the light's wavelength doubles too. If the universe was 1/10 its current size when the photon began its journey, the wavelength is stretched by a factor of 10 by the time it arrives. This is why cosmologists often describe redshift in terms of scale factor. The scale factor is a number that tells you how big the universe is relative to today. If today's size is written as a number 1, and the universe at some earlier point was 1/3 that size, the scale factor at that earlier time was 0.33. The relationship between redshift and scale factor is simple and exact. 1 plus z equals 1 divided by the scale factor at emission. If you detect a galaxy at redshift 5, that means the universe was 1/6. Its current size when the light left. If you see something at redshift 10, the universe was 1/11 its current size. Redshift is therefore a direct measurement of cosmic history. It tells you what era the galaxy belongs to, even before you know anything about its properties. This makes redshift incredibly valuable. It's a time machine marker. You can't tell how old a galaxy is by looking at it, but you can tell when the light began its journey. That gives you a foothold for everything else. When its stars formed, what the universe looked like at that era, how local gas behaved, and how the galaxy fits into the story of cosmic structure. But redshift also misleads people in several ways. One common misunderstanding is the idea that higher redshift always means farther. That's mostly true for galaxies within the observable universe today. But the relationship between redshift and distance is anything but linear. The first step up in redshift, from 0 to 1, corresponds to a certain amount of distance. The next step, from 1 to 2, adds less. From 5 to 6, even less. Redshift compresses physical distances at the high end because space isn't expanding at a constant rate over time. The farther back you go, the faster the universe was changing. You're not just looking farther away, you're looking into epochs when expansion behaved differently. This is why redshift is often described as fossil information about cosmic expansion. Each photon carries a record of how much stretching occurred during its journey. By comparing many photons from many distances, astronomers can reconstruct how the universe changed over billions of years. This is how we know the expansion has accelerated recently and was slowing down much earlier. Redshift is the thread that ties these eras together. Another subtlety is that redshift isn't always caused by expansion. Gravity can also stretch light, a phenomenon called gravitational redshift. If a photon climbs out of a deep gravitational well near a dense star or a black hole, it loses energy and its wavelength stretches. This has nothing to do with cosmic expansion. Astronomers measure gravitational redshift to study extreme objects like neutron stars and black holes. It's small compared to cosmic redshift for distant galaxies, but it matters in specific environments. For example, clocks placed at different altitudes on Earth tick at slightly different rates due to gravitational redshift. something GPS satellites must correct for constantly. Then there's the issue of peculiar motion. Even though expansion dominates motion at very large scales, galaxies still move around within their local environment due to gravity. These motions add a small Doppler shift on top of the cosmic redshift. For nearby galaxies, peculiar motion can be a major part of their redshift. For galaxies far away, it's a tiny perturbation. But ignoring peculiar motion can skew measurements when you're mapping the large-scale cosmic web. Cosmologists have to account for this when interpreting redshift surveys. One of the trickiest points is how redshift interacts with photon energy. When a photon is stretched by expansion, the wavelength increases, which means the energy drops. This isn't because the photon slows down, it still travels at the speed of light, but because the universe dilutes its energy by expanding. You can picture it like a wave being stretched on an inflating balloon. The wave spreads out, so its peaks become farther apart. Redshift literally drains energy from light. That's part of why distant galaxies appear so faint. Even if they emitted an intense burst of light, expansion weakens it over time. This effect compounds with ordinary dimming from distance, making the deepest objects extremely faint. You might think this energy loss violates some conservation law, but it doesn't. The universe doesn't conserve energy globally in the simple way we're used to from isolated systems. Energy conservation still applies locally, but when space-time itself evolves, that rule expands with it. Redshift is one of the clearest snapshots of that counterintuitive behavior. Light loses energy because space-time grows, not because something is doing work on it. A related confusion appears when people try to convert redshift directly into distance using online calculators. These tools are useful, but they hide how much physics sits inside the translation. To convert redshift to distance, you need a model of the universe: the expansion rate, the contribution of matter, the contribution of dark energy, and the way those contributions evolve. Change those numbers slightly, and the distance shifts. If you change the underlying physics, say if dark energy behaved differently than currently thought, the conversion would change significantly. Redshift itself doesn't change, but its relationship to distance does. That's why cosmologists talk so much about cosmological parameters. Redshift is the observable. The distances are interpretations. Redshift also plays a crucial role in how telescopes are designed. When you see an image from the James Webb Space Telescope showing a galaxy at redshift 10 or higher, you're not seeing visible light from that galaxy. That light has been stretched into the infrared by expansion. So Webb is built to detect infrared photons because that's where ancient light ends up. Hubble, which is optimized for visible and near-infrared light, could only see galaxies out to certain redshifts before their light became too stretched to detect. Redshift dictates what wavelengths telescopes must target. This shift has another consequence. The farther you look, the less you're seeing galaxies as they look now. Their ultraviolet light becomes visible light. Their visible light becomes infrared. Their infrared becomes microwaves. If you looked at a galaxy at redshift 15 with your eyes, assuming they could somehow detect the nearly infrared range photons reaching you, it would appear nothing like its present-day counterpart. You're seeing a distorted, stretched version of its true spectrum, modified by the universe itself. Redshift forces astronomers to reconstruct what the original light would have been, correcting for billions of years of stretching. Without that correction, you couldn't compare galaxies across cosmic time. One of the most astonishing things redshift reveals is the shape of the observable universe. By mapping redshift across tens of thousands of galaxies, scientists discovered that the universe is not only expanding, but doing so in a way that lines up with Einstein's equations for a uniform, isotropic cosmology. Redshift surveys show the large-scale cosmic web, clusters, filaments, voids woven into structure. They show how galaxies clump under gravity. They show how expansion smooths the universe on large scales. None of that would be visible without redshift as the basic coordinate system. This makes redshift far more than a curiosity. It's the foundation of observational cosmology. Every measurement of early galaxies, every map of large-scale structure, every estimate of the expansion rate, and every reconstruction of the universe's history relies on it. Without redshift, we'd know almost nothing about how the universe evolved. Yet it remains a source of confusion precisely because it compresses so much information into a single number. It's easy to oversimplify. Some people treat redshift as distance. Others treat it as velocity. Others think it describes the speed of expansion. In reality, redshift doesn't directly measure any of those. It measures the ratio between the size of the universe at emission and now. Everything else is interpretation. The beauty of redshift is that it contains the raw imprint of cosmic evolution. It's the universe marking each photon with a timestamp. But to read that timestamp correctly, you have to understand what it encodes and what it doesn't. If you've ever fallen down the rabbit hole of cosmology articles, you've probably seen terms like co-moving distance, proper distance, look-back time, light travel distance, and angular diameter distance. They all sound like different ways of answering the same question. How far away is something? But in cosmology, that question doesn't have a single answer. There is no one true distance to a galaxy billions of light years away, because that concept breaks down when the space between you and the object is stretching while you're trying to measure it. This is where people usually get frustrated, because in everyday life, distance is simple. You can walk to a building. You can measure how far it is with a tape measure or a map. None of that intuition transfers cleanly to a universe where distances evolve as you look at them. What astronomers do instead is define several distances, each one answering a specific question. None of them replace the others. They sit side by side like different tools in a toolbox, and understanding why all these distances exist goes a long way toward understanding why light years break our brains when you push them far enough. Let's start with the most natural distance, the light travel distance. If a galaxy's light took 13 billion years to reach us, you might think the galaxy is 13 billion light years away. That's not wrong, but it's incomplete. Light travel time only tells you how long the photon was in flight. During those 13 billion years, the universe didn't sit still. It expanded dramatically. So the galaxy you're observing isn't sitting where it was when the photon left. By the time the light arrives, the space between you and that galaxy has stretched so much that the galaxy is now vastly farther away, sometimes more than twice or 3 times the light travel distance. So while 13 billion light years is a real number, it doesn't answer the question, how far away is the galaxy right now? To answer that question, astronomers use the proper distance. This is the distance between 2 points measured at a specific moment in cosmic time. If you could freeze the expansion of the universe right now, just hit pause, and measure the length of the cosmic ruler between Earth and that distant galaxy, you would get the proper distance today. For most of the farthest galaxies we've seen, the proper distance is much larger than the light travel distance. A galaxy whose light has been traveling for around 13 billion years might have a proper distance today of over 30 billion light years. That gap is entirely due to expansion while the photon was moving. But here's the catch. Proper distance changes with time. The same galaxy's proper distance 10 billion years ago, 5 billion years ago, or today are all different numbers. So even though proper distance answers the question, how far is the galaxy right now, it's not a stable property of the galaxy. The number grows as the universe expands, and for extremely distant galaxies, that growth is significant. This is where co-moving distance comes in, the version cosmologists rely on most heavily in their calculations. Co-moving distance strips away the expansion entirely. Instead of measuring current physical separation, it measures the separation in units that expand with the universe. Imagine the universe as a giant grid printed on an elastic sheet. Co-moving distance tells you how many grid cells sit between 2 objects. Even as the sheet stretches, the number of cells stays the same. So co-moving distance never changes, even though proper distance does. For cosmologists who want stable coordinates that don't evolve as the universe grows, co-moving distance is essential. It's the fixed scaffolding on which the entire structure of the cosmic web is mapped. None of this is about redefining reality to make math easier. It's about describing a universe where the basic stage itself changes size. If you try to use one single type of distance for all purposes, you would get contradictions everywhere. Look-back time is perfect if you want to talk about history. Proper distance is perfect if you want to talk about where things are right now. Co-moving distance is perfect if you want a stable coordinate system. There's no best one. They each answer different questions. Another distance that confuses people is the angular diameter distance. This one exists because astronomers often measure size through angles. If you know how big an object truly is, for example, a certain type of galaxy cluster, and you measure the angle it spans on the sky, you can infer its distance. But in an expanding universe, geometry is distorted by the growth of space. An object at a greater redshift doesn't necessarily appear smaller in a simple linear way. In fact, there's a point where farther objects begin to look larger rather than smaller. This sounds impossible until you remember that when the light left the distant galaxy, the universe was much smaller. The galaxy was physically closer when it emitted its light. The fact that it has receded to a much larger distance by the time the light arrives doesn't change the geometry of the moment the light was emitted. So there's a turning point. Beyond a redshift of around 1.5, objects actually start appearing larger as their redshift increases. Angular diameter distance captures this very non-intuitive behavior. A related quantity is the luminosity distance. This one deals with how bright an object appears. If the universe were static, brightness would follow a simple inverse square law, double the distance, and the object looks 4 times fainter. But expansion changes things. Light gets stretched, losing energy, and the arrival rate of photons slows. So cosmologists define luminosity distance to fold all of that into a single effective number, essentially the distance you would infer if the universe weren't expanding. This is how type Ia supernovae became such powerful tools. By comparing their measured brightness to the expected brightness, cosmologists can extract the luminosity distance and use it to probe cosmic expansion. This method led to the discovery in 1998 that the expansion of the universe is accelerating. The important point here is that each distance is tailored to a specific observational context. That might sound messy, but trying to force everything into a single distance makes far less sense in an expanding universe. Everyday distance concepts assume a static arena, but in cosmology the arena is stretching and space itself participates in the story. The different distances aren't tricks, they're translations of a single underlying picture: light, traveling through a growing space-time. To understand why the distinctions matter, think about what a cosmologist actually needs to do. They might want to calculate how big a galaxy cluster appears on the sky. For that, they need angular diameter distance. They might want to know how many galaxies occupy a certain chunk of the universe. For that, co-moving distance is perfect. They might want to model how much light from a distant supernova has dimmed on its way to Earth. That requires luminosity distance. And if they want to trace the universe's timeline, they use look-back time. Each distance is a different lens on the same reality. Trying to fold them together would blur the physics instead of clarifying it. And one of the biggest misconceptions people have is thinking the distance to a galaxy is a fixed piece of information. But the farther out you look, the less this idea works. When you observe a galaxy at high redshift, you're engaging with 3 different distances at once. You know how long ago the light was emitted, you know how far away the galaxy is right now, and you know how separate the galaxy is in the coordinate system that expands with the universe. All 3 describe the same event, the photon leaving the galaxy and arriving at your telescope, but they emphasize different parts of the story. To see why this matters, imagine an object whose light took 12 billion years to reach us. That number is straightforward enough, but the proper distance to that object today might be over 25 billion light years. That's not because the object moved away at impossible speeds, it's because the space between you and the object kept expanding during the entire journey. And the co-moving distance might be around 30 billion light years, meaning if you froze the expansion at any time, the number of cosmic grid cells between you and that object stays constant. You could ask which one is the real distance. The honest answer is all of them, depending on which question you're asking. This is exactly why cosmology textbooks spend so much time on the metric, the mathematical expression that describes how distances work in a curved, expanding universe. You don't need to dive into the math to understand the idea. The metric tells you that distances depend on time because the universe itself evolves. So any measurement tied to light or mass or geometry has to take that evolution into account. The different distance measures are just different ways of interpreting a single expanding reality. There's something else that makes these distances feel counterintuitive: the horizon problem. Because the universe has a finite age and light has a finite speed, we can only see so far. But the edge of the observable universe isn't defined by distance, it's defined by time. We can't see beyond the moment when the first neutral atoms formed and the universe became transparent. Light from earlier than that simply couldn't travel freely. That moment happened about 380,000 years after the Big Bang. And the proper distance to that surface of last scattering today is about 46 billion light-years. Not because anything moved faster than light, but because expansion carried everything apart. This number, 46 billion light-years, is a good example of how misleading simple intuition can be. You'd think the maximum observable distance would be 13.8 billion light-years, the age of the universe. But proper distance and look-back time aren't the same thing. Expansion stretches the distance to the earliest observable regions, far beyond the number of years you're looking back. It helps to think of distances in cosmology like different translations of a foreign phrase. Look-back time is the literal translation. Proper distance is the translation you use when you want to understand the present tense meaning. Commoving distance is the translation for technical discussions where consistency matters more than simplicity. They're all describing the same idea in different ways. The final layer of confusion comes from the fact that all these distances depend on the cosmological model. If you change the expansion rate or the amount of dark matter or the behavior of dark energy, the distances shift. But redshift, the raw observable, does not. Redshift is the anchor. The distances are the interpretations. This is one reason cosmologists are so obsessed with measuring the expansion rate precisely. Every distance in the universe hinges on those parameters. So when you see a headline saying a galaxy is 33 billion light-years away, that number is the proper distance today. If the same article says the galaxy's light took 13 billion years to reach us, that's the look-back time. And if a research paper lists the galaxy's position as 32 billion light-years co-moving, that's the constant coordinate distance in the expanding universe. All three numbers describe the same galaxy, and none of them contradict each other. In a non-expanding universe, these values would all collapse into one. But we don't live in that kind of universe. We live in one where space grows, light stretches, and even simple questions like how far away is that have layered answers. This isn't a flaw in the theory, it's a direct consequence of the most basic observational fact we have. Our universe is expanding. Cosmic horizons are one of the strangest consequences of living in an expanding universe. They tell us that some regions of space are not just far away, they are permanently disconnected from us. No signal from here can ever reach them, and no signal from them can ever reach here. Even if you sat around for 1 trillion years with the best telescope imaginable, even if you watch the universe expand and cool and evolve, certain galaxies will always remain invisible. They're beyond a boundary built into space-time itself. This is where our everyday sense of distance completely fails. If something is far away but not infinitely far, you assume you could get closer to it if you kept moving long enough. That idea simply isn't true on cosmic scales. Expansion can overwhelm motion. It can stretch the space between 2 points at a rate that makes catching up impossible, even at the speed of light. Cosmic horizons define that limit. To get a handle on this, it helps to separate two different horizons that people often mix up: the particle horizon and the event horizon. They sound similar, but they describe two very different limits on what we can know and what we can ever influence. The particle horizon is the boundary of the observable universe, the farthest distance from which light has had time to reach us since the beginning. It's not defined by distance, but by time. The universe has been transparent since about 380,000 years after the Big Bang. Before that, photons were constantly scattered by charged particles, creating an opaque fog. So even in principle, light from earlier than that can't reach us. That moment, when the fog cleared and photons began traveling freely, is the earliest possible light we can observe. And those photons have been stretching and traveling for 13.8 billion years. But because the universe has expanded dramatically during that journey, the proper distance to the region they came from isn't 13.8 billion light-years. It's around 46 billion light-years. That's our particle horizon right now. Anything beyond that distance has simply not had enough time to send light to us. The light exists, but it's still on the way and will never catch up, because expansion keeps pushing the source farther apart. What makes this horizon strange is that it grows every year. The longer the universe ages, the more light from slightly farther regions can reach us. The particle horizon marks the limit of what we can observe today, but it isn't a fixed barrier. With time, more of the universe becomes visible. The event horizon, on the other hand, is a very different kind of limit. It marks the region that will never, under any circumstances, be able to influence us. Even if the universe lasts forever, even if we wait trillions or quadrillions of years, the event horizon will always remain a hard boundary. Anything outside it is causally disconnected from us, not temporarily, but permanently. This difference between cannot see yet and cannot ever communicate is subtle but important. The particle horizon is about the past. The event horizon is about the future. The reason the event horizon exists has everything to do with cosmic acceleration. In the late 1990s, observations of distant supernovae revealed that the expansion of the universe isn't slowing down, it's speeding up. Something, which we label as dark energy, is causing the expansion to accelerate. When expansion accelerates, distant galaxies move away from us faster over time, not slower. And eventually, the expansion becomes so dominant that light emitted from beyond a certain distance will never make progress toward us. No matter how long you wait, the expansion stretches space faster than the photon can move through it. You can picture this with a treadmill analogy. Imagine running toward a point on a treadmill that keeps speeding up. If the treadmill's speed rises faster than you can accelerate, you'll never reach the point no matter how hard you run. In an accelerating universe, light from beyond the event horizon is like a runner on a treadmill that's speeding up beneath it. The light moves at a constant speed, but the ground of space stretches faster and faster, so the photon never gets any closer. When cosmologists talk about the far future of the universe, this event horizon becomes the defining limit of what remains visible. The observable universe won't stay 46 billion light-years in radius. It will eventually freeze into a much smaller region of isolated galaxies, all the others redshifting into invisibility. Over time, only galaxies gravitationally bound to the Milky Way's local group will remain. Everything else will fade beyond reach, not because it's truly disappearing, but because the expansion will have carried it beyond our event horizon. We often think of the universe as something we can keep exploring indefinitely, as long as we develop better technology, better telescopes, better propulsion systems. The truth is that technology doesn't matter here. No amount of engineering can overcome the structure of space-time itself. Once a region moves outside the event horizon, it is gone forever from our cosmic neighborhood. There's another horizon that shows up in discussions, the Hubble radius. This is not a true horizon, but people often mistake it for one. The Hubble radius is simply the distance at which recession velocity equals the speed of light, right now around 14.4 billion light-years. That means any galaxy beyond that distance is receding faster than light due to expansion. But receding faster than light does not mean unreachable. Light from some galaxies beyond the Hubble radius can still reach us if the expansion rate changes in such a way that the photon eventually enters a region of slower stretching. This actually happens for many galaxies whose light we see today. They were receding faster than light when the photons left, but the expansion slowed enough for those photons to make progress. The true permanent barrier is the event horizon, not the Hubble radius. The event horizon depends on future expansion. The Hubble radius is just a snapshot of today's conditions. As long as expansion accelerates, the event horizon will remain smaller than the particle horizon and will shrink in comoving terms. More galaxies will slip beyond it over time, even ones that are currently visible. This paints a strange picture. Every year we see more of the early universe because the particle horizon grows, but we permanently lose access to more of the distant universe because the event horizon shrinks. It's like gaining memories of the past while losing contact with the present. There's another way to think about cosmic horizons that makes the concept even clearer. Imagine drawing a world line for Earth, its path through space-time. Then imagine drawing the world line of a distant galaxy. If the expansion is slowing, the two world lines gradually converge. Light from the galaxy continues reaching us, and we continue gaining access to more of its history. But if the expansion is accelerating, the world lines tilt away from each other. Eventually, no light emitted after a certain moment ever intersects our world line. That moment defines the event horizon. This isn't just theoretical. Observations show that about 94% of the galaxies currently inside the observable universe are already beyond our event horizon. They remain visible now because we're still receiving ancient light from them. But any light they emit today, any supernova, any collision, any change, will never reach us. We are seeing their ancient past, but their present and future are permanently out of reach. This also means that if humanity ever built a starship capable of traveling at close to the speed of light, And if it tried to reach certain galaxies, it wouldn't matter how early the launch happened. The galaxy would be receding too fast, and the ship would never close the gap. There is no trajectory that reaches galaxies beyond the event horizon, because motion through space cannot compete with the growth of space itself. This doesn't make the universe smaller, it makes it stranger. It tells us that reachable and visible are two different concepts. A galaxy can be visible and unreachable at the same time. A galaxy can be permanently out of contact even while its ancient light shines into our telescopes. And the universe can contain regions that are forever separate from one another, not due to obstacles, but due to the geometry of space-time. The biggest consequence of cosmic horizons is how they frame the future of the observable universe. Over time, every galaxy outside the local group will redshift to such extreme wavelengths that they fade entirely. The night sky, billions of years from now, will not be filled with countless galaxies. It will be a sparse place, dominated by the stars within our local gravitational island. Future astronomers who emerge in that distant era would have no way of inferring that the universe ever contained other galaxies. Every clue pointing to expansion, dark energy, and the large-scale structure would be erased by time. They would see a small, static, cosmic neighborhood and nothing more. This isn't just a curiosity, it defines what information is fundamentally accessible. The universe is vast, but the part we can ever interact with is limited by these horizons. They divide the universe into regions with no possible communication, no shared physics, and no common future. Horizons aren't just about what we can't see, they're about what we can't ever influence or touch. And that's a profound idea. The universe contains far more than we can observe, but it also contains far more than we can even potentially observe. When people first hear that the universe is expanding, they often imagine an explosion, something like a fireball erupting into empty space, flinging galaxies outward. It's an understandable picture because explosions are familiar and expansion sounds like outward motion. But this mental model creates confusion almost instantly. It forces you to ask questions that don't actually make sense in cosmology. What did it explode into? Where is the center? Are we near the edge? If everything started in one spot, how can every galaxy see every other galaxy moving away? Every one of those questions comes from treating expansion as an explosion instead of what it truly is, a stretching of space-time itself. And once you replace the explosion idea with the expansion idea, a lot of cosmology suddenly becomes much less mysterious. Start with the core misunderstanding. Explosions need a location. If a bomb goes off in an empty field, you can point to the spot where it exploded. You can mark the center. You can draw expanding shock waves that move outward through air. But the Big Bang didn't happen in a pre-existing void. There was no outside. There was no empty space waiting for the universe to fill it. Space was part of the universe from the beginning, and the Big Bang marks the earliest moment when the densities and temperatures were high enough to define the form of the universe we know. It's not an explosion in space, it's the rapid expansion of space. To get a better grip on this, imagine a coordinate grid drawn on a rubber sheet. If you stretch the sheet in every direction, the distance between every pair of points increases. No point on the sheet is special. Nothing explodes outward from a center. The stretching happens everywhere, and the stretching itself is the evolution. That's closer to how the universe expands. Galaxies aren't flying through space like debris. They're mostly sitting still in their local patches of space, while the space between them grows. This is why every galaxy sees every other galaxy receding. Not because everything was thrown away from a center, but because the separation between all unbound galaxies increases over time. If you pick any galaxy and observe long enough, you'll notice the same pattern we see from Earth. Distant galaxies drifting away, with the most distant receding the fastest. That's exactly what you'd expect on a uniformly stretching surface. Understanding this difference also explains why there is no edge. If you imagine an explosion, you imagine a boundary where the matter ends and empty space begins. But if space itself is expanding, that boundary doesn't exist. The universe doesn't grow into anything. It grows by enlarging its own geometry. A better way to phrase it is that the distances within the universe increase. The universe itself doesn't expand into something external. This distinction also clears up the question of whether we are in a special place. In an explosion model, being close to the center would make you see a different pattern of motion than being on the edge. But astronomers everywhere, no matter where they would hypothetically stand, would see the same pattern of expansion because the effect is uniform. That's a direct result of the universe being homogeneous and isotropic on large scales. No spot is special because nothing is moving away from a unique center. The expansion doesn't have a privileged point. You can walk this idea forward and see why galaxies don't get ripped apart. If space is stretching, shouldn't everything stretch? Shouldn't stars get farther from planets and atoms get torn in half? The answer is no, because expansion only dominates where gravity, or in other cases, electromagnetic or nuclear forces, is too weak to hold things together. Galaxies are held together by their own gravity. Solar systems are bound even more tightly. Atoms are bound incomparably more tightly. Expansion operates on the large-scale structure of the universe, not on locally bound systems. A simple way to picture this is to think of raisins in dough. If you let dough rise, the raisins spread apart. The dough expands, but the raisins don't stretch because they're held together by their own internal cohesion. Galaxies are the raisins, the universe is the dough. One reason the explosion analogy falls apart is that it implies momentum-driven motion. You might imagine galaxies shot outward in the Big Bang with incredible speed, gradually slowing as time passes. But the early universe didn't start with galaxies. It started with a hot, dense, nearly uniform plasma. And the expansion wasn't driven by things moving outward. It was driven by the dynamics of space-time itself. Later, when matter clumped together into galaxies, they inherited the overall expansion pattern. They didn't start with explosive outward velocities, they simply drifted apart as the underlying space grew. This is why some galaxies appear to recede faster than light. If they were actually moving through space at that speed, it would violate relativity. But they're not. Their separation increases faster than light because the space between us expands faster than light, and relativity places no speed limit on the expansion of space itself. The speed limit applies only to motion through space. Once you drop the explosion idea, superluminal recession stops seeming like a contradiction. And another way this shift in thinking helps is with the question of redshift. If galaxies were racing away through space like shrapnel from an explosion, the redshift we observe would be purely Doppler, a simple wavelength stretching from relative motion. But cosmological redshift is different. It comes from the expansion of space, not from galaxies accelerating through it. A photon's wavelength grows because the space it travels through stretches. This distinction matters because it means we can directly measure how the universe has grown by looking at the light we receive. There's also the feeling people often have that the Big Bang must have been a happening in one point. This image usually comes from imagining the early universe being incredibly small, dense, and hot. If you roll the universe backward in time, everything gets closer together, but that doesn't mean everything was compressed into a single tiny spot in a larger space. Instead, the entire space itself shrinks. The whole universe, whatever size it had, gets smaller together. It doesn't collapse into a center the way matter collapses into the center of an explosion. Every region of space contracts toward every other region. That's why we say the Big Bang happened everywhere. Not because the universe was infinitely large at the beginning, but because every point in the universe today corresponds to some region that was part of the early hot, dense state. The Big Bang isn't a point in space, it's a moment in time. Thinking of expansion instead of explosion also helps with understanding why expansion looks uniform. If matter had been thrown outward, you'd expect clumps and irregularities like the irregular splatter of an actual explosion. Instead, the early universe was astonishingly smooth. The variations in density were tiny, only 1 part in 100,000. Those small fluctuations eventually grew into galaxies and clusters, but the uniformity itself is a fingerprint of expansion, not an outward blast. Another point that becomes much clearer once you drop the explosion analogy is that expansion has no preferred direction. In an explosion, matter expands outward along a vector. You can draw arrows showing the trajectories. Expansion doesn't work that way. No matter where you stand, galaxies recede radially outward from you. And someone in a galaxy a billion light years away would see the same pattern. This cannot happen in an explosion without placing you at the exact center. But in an expanding universe, Every point can be treated as the center because the expansion is symmetrical everywhere. This distinction also solves the question of getting to the edge. In an explosion, you could imagine catching up to the expanding debris, if you could move fast enough. But because the universe has no boundary, there is nothing to reach. You can move from galaxy to galaxy, but you will never find an edge where matter stops. You will only find more space. And beyond that space lies more space. The universe could be finite or infinite in size, we don't know, but in either case, it doesn't have an edge you could run into. That idea only exists if you treat it like an explosion. There's another subtle misunderstanding hidden inside the explosion picture, the idea that the universe expands from something into emptiness. But the universe doesn't grow because something inside it exerts pressure outward. It grows because the overall fabric of space-time evolves. The equations of general relativity allow the scale of space to change over time. Once matter and radiation fill that evolving space-time, the distances between them naturally increase as the scale grows. If you imagine the universe today, pick any two faraway galaxies. Those galaxies aren't pushing away from each other. They're like two marks on a balloon. When the balloon inflates, the marks separate. Their separation is a property of the geometry, not of their individual behavior, and that's why expansion doesn't slow down the same way an explosion would. When you throw something outward, it gradually decelerates. But if space itself drives the separation, the behavior depends on what fills the universe: radiation, matter, dark energy, and how those components evolve. In the early universe, expansion slowed because matter and radiation dominated. But in recent cosmological history, dark energy took over. And because dark energy behaves like a constant energy density per unit volume, the more space there is, the more total dark energy exists. This causes expansion to accelerate, which is the opposite of an explosion fading over time. The explosion analogy has no mechanism for accelerating expansion. The real universe does. One last reason the explosion model is misleading is that it makes people think the Big Bang was a chaotic detonation. But the early universe was nearly smooth, extremely uniform, and governed by simple physical laws. The chaos came later as tiny irregularities grew into stars and galaxies. The explosion picture swaps the timeline. It makes you think disorder came first and structure emerged second. In reality, structure emerged out of a smooth beginning. If you try to cling to the explosion analogy, nearly every part of cosmology seems contradictory or overcomplicated. Once you see expansion for what it truly is, the growth of space itself, everything becomes much more consistent. Redshift makes sense. No center of the universe makes sense. Horizons make sense. The apparent superluminal motion makes sense. The large-scale uniformity makes sense. And the shape of the observable universe becomes something physical, not something you have to force into a mental image of debris flying outward. The surprising thing is that abandoning the explosion analogy doesn't make the universe more abstract. It makes it clearer. The real version is stranger, yes, but not harder to understand. You don't have to picture a blast, you only have to picture distances growing. At first glance, the numbers don't line up. If the universe is about 13.8 billion years old, then you'd expect the farthest light we could possibly see to come from 13.8 billion light years away. After all, light can't outrun time. But every modern measurement tells us the radius of the observable universe is roughly 46 billion light years. Not 13.8, not 20, not even close. 46. And that number isn't a mistake or some hand-wavy choice of units. It's what falls out of well-understood physics combined with the way space itself evolves. If this feels like distance cheating, that's because our instincts about distance and time were trained inside a world where space stays put. If you throw a ball, the distance it travels depends only on speed and time. If light leaves a star, we instinctively think it works the same way, just faster. But the universe doesn't operate like a fixed stage. Space stretches. While light is on its way to us, the path it's traveling expands underneath it. That stretching doesn't slow the light down. It still moves locally at the speed of light, but it lengthens the distance the photon ends up covering. Imagine trying to walk across a moving walkway that's expanding as you walk. You move forward at your normal pace, but the walkway itself keeps growing, adding new length between you and the place you're trying to reach. If If the walkway doubles in length while you're crossing it, you cover more ground than the simple equation speed times time would predict. Something similar happens to photons crossing the early universe, except instead of a mechanical walkway, it's the fabric of the cosmos. To understand why the observable universe reaches 46 billion light-years, you have to follow the photon's journey from their earliest observable moment, the cosmic microwave background, released roughly 380,000 years after the Big Bang. Before that moment, the universe was too hot and dense for light to travel freely. Photons kept bouncing off charged particles, forming a kind of fog. When the temperature dropped enough for electrons to bind with protons, the fog cleared. From that moment onward, light could move in straight lines. Those first free photons have been traveling toward us ever since, but their path has been stretched again and again as the universe expanded. The key thing is that while the light was en route, the universe didn't just grow gently, it expanded enormously. In the early years, expansion was slowing down because radiation and matter dominated the energy density. Later, dark energy took over and the expansion began accelerating. Every phase added more distance to the photon's total journey. An important detail here is that photons don't leave from a fixed location that stays put while they travel. The point where the cosmic microwave background was emitted isn't still 13.8 billion light-years away. That point has been carried outward by the expansion of space. So the photon has been chasing a destination that's retreating at the same time. When we detect that light today, we're seeing photons that originated from a region that's now about 46 billion light-years from us. This is what cosmologists call the co-moving distance. It's the proper distance between 2 points measured at a single moment in cosmic time. If you could freeze the universe right now, the farthest part of space from which light could have reached us since the beginning would lie roughly 46 billion light-years away. The number isn't the age of the universe multiplied by the speed of light. It's the age of the universe multiplied by the speed of light, plus all the stretching of space that occurred during the journey. This is also why the observable universe is a sphere around us, not because we're in a privileged place, but because light has had a limited amount of time to reach us. Any observer anywhere in the universe would find themselves at the center of their own observable bubble. That bubble is defined not by geography, but by the reach of light through expanding space. It's worth stopping for a moment to think about what observable really means. It isn't the whole universe. It's only the region from which light has had time to arrive. Beyond that boundary, there's more universe we can't see yet, not because it isn't there, but because the signals haven't reached us. And because the expansion is accelerating, some regions will never become visible, no matter how long we wait. The expansion of space can outpace the ability of light to close the gap. This is where the concept of the cosmic light horizon matters. If you track the speed of expansion at different distances, you find a region far enough away that space is expanding faster than light could ever cross. That doesn't violate relativity because it's not motion through space. It's the metric of space changing, but it creates a sort of dynamic boundary, the horizon line separating the regions we could eventually see from those we never will. Some people take this and imagine the universe as a huge bubble with a physical shell at 46 billion light-years. That's not it. There's no wall there. There's no change in matter or energy density. The boundary is only a limit in time, the slice of space whose photons have finally had enough cosmic history to reach us. If you could place a galaxy right at that distance and pause the expansion, it would look perfectly normal. It isn't at the edge of anything, it's simply the most distant region that light has had time to bridge, and that region changes as time moves forward. A billion years from now, the observable universe will be larger in terms of what light has had time to traverse. But it won't grow by the full amount you might expect because accelerating expansion continues to pull certain regions out of reach. There's a tug-of-war between the passage of time, which adds more to our observable bubble, and dark energy, which removes distant regions by pushing them beyond the horizon. The result is a steadily shifting balance where the observable universe evolves, but not in a simple linear way. Another point people often miss is that the 46 billion light-year radius doesn't describe how far the oldest light traveled in its own frame. Photons don't experience time. They don't have an internal clock. But if you imagine the distance from their perspective as a path through expanding space, it's not a clean trajectory. The wavelength of that light has stretched by a factor of over 1,000 since it was emitted. That's why the cosmic microwave background is now in the microwave part of the spectrum instead of visible light. Every pulse of expansion elongated it. This stretching of wavelength is directly connected to the stretching of distance. You can measure the expansion history of the universe by measuring how much the wavelength has been stretched. That relationship is an important reason why cosmologists trust the 46 billion light-year figure. It isn't pulled from a single model, it falls out of multiple independent measurements. Redshift data, the shape of the cosmic microwave background, the distribution of galaxies, and the behavior of Type 1a supernova. There's one more subtlety that helps the whole picture snap into place. Even though the observable universe is 46 billion light-years in radius, the regions near that boundary don't look like they did when the photons left. When we observe a galaxy 10 billion light-years away, we see it as it was 10 billion years ago. But in reality, that galaxy is now much farther away because the universe kept expanding during the photon's travel. The deeper you look, the more out of date your view becomes. So the cosmic microwave background isn't the edge of the universe. It's just the oldest light we can see, frozen in time from a region that has since migrated tens of billions of light-years farther out. This idea that the universe has grown so dramatically while photons were en route helps connect several other concepts that seem confusing at first. It clarifies why we can see galaxies with redshifts so large they imply superluminal recession. It clarifies why the early universe appears so uniform, even though it's so large, and it clarifies why expansion can outpace light without breaking relativity. The biggest takeaway is that distance in cosmology isn't static. You can't measure it the way you measure a road or a coastline. Cosmological distance is dynamic, tied to the history of expansion. Once you accept that, the 46 billion light-year radius of the observable universe feels less like a contradiction and more like a natural result of billions of years of stretching. When people hear that the observable universe has a radius of about 46 billion light-years, the next question usually comes quickly. What's outside that? It feels like there must be some kind of outer zone, another shell of galaxies, or a region where matter thins out, or maybe even a literal edge where space stops. But none of that reflects what cosmologists actually mean when they talk about beyond the observable universe. The phrase isn't about a boundary in space at all, it's about a limit in time and causality. And once you unpack that idea, you realize the part we can see is probably a tiny fraction of something much larger, maybe unimaginably larger, and possibly even infinite. Start with the simplest version. The observable universe is limited by how long light has had to reach us. That's it. There's no wall, no edge, no boundary where matter ends. The only thing defining the observable region is whether a photon has had time to make the trip. Anything farther away than that hasn't had the chance. It's not censored. It's not blocked. It's just too far for light to have connected the dots across 13.8 billion years while the space between kept expanding. A good way to picture this is to imagine sitting in the middle of a huge field on a foggy morning. If the fog is thick enough, you can only see a few meters in every direction. That circular patch of visibility isn't the whole field. It's just what the fog allows you to observe. The field extends far beyond your view. If the fog lifted, you'd see more. But in cosmology, the fog is time itself. You can't lift it. You can only wait, and waiting doesn't guarantee much because the expansion of space keeps dragging distant regions farther out. Once you shift to this time-based view, the phrase beyond the observable universe becomes easier to understand. It's simply the region whose light hasn't arrived yet. And here's where things get interesting. Everything suggests that the same cosmic conditions that created our observable patch continue beyond it. The universe doesn't suddenly change outside the 46 billion light-year radius. The physics doesn't flip. The distribution of matter doesn't break into some strange alternate pattern. On large scales, space looks statistically the same everywhere we examine. So the simplest assumption, the one that requires the fewest special conditions, is that the universe continues in the same style past the limits of what we can see. This assumption is so fundamental that cosmologists gave it a name, the cosmological principle. It says that on large enough scales, the universe is homogeneous, same ingredients everywhere, and isotropic, looks the same in every direction. We didn't invent this principle because it felt right. Observations strongly support it. The cosmic microwave background is nearly uniform across the sky. Galaxies are arranged in a web-like structure that looks consistent no matter which direction you look. And the statistical properties of matter, its density, temperature variations, and fluctuation patterns, line up with what you'd expect from a universe that doesn't have special zones or privileged locations. If this pattern holds, then there's no reason to expect the universe to stop at 46 billion light-years. That's just the edge of our visibility, not the edge of the cosmos. But how much bigger might the universe be? Here is where things get tricky because our observational access ends abruptly at the horizon. We can infer, estimate, and model, but we can't directly confirm anything beyond that limit. Yet several lines of evidence hint at a universe that is at least much larger than the observable part, and possibly infinite. And one of the most compelling clues comes from the shape of space itself. When cosmologists measure the geometry of the universe, they're essentially checking whether space is curved or flat on the largest scales. Positive curvature would mean the universe bends like the surface of a sphere. Negative curvature means it bends like a saddle. Zero curvature means it's flat. Each shape tells you something about the universe's total size. Over the past couple of decades, increasingly precise measurements, especially of the cosmic microwave background, have shown that the universe is extremely close to flat. Not perfectly flat to the last decimal, but so close that if it does curve, the curvature radius must be far larger than the observable universe. If space were curved like a sphere on scales close to what we can see, the cosmic microwave background would show specific distortions. But it doesn't. The patterns in the background radiation look exactly like what you'd expect in a universe with extremely mild or zero curvature. A nearly flat universe could, in principle, still be finite. But if it is finite, it's much larger than the part we can see, larger by hundreds or thousands of times. You can have a sphere where the surface is so big that walking a tiny patch feels like flat land. The same logic applies to cosmology. The visible part of the universe might just be too small to reveal the overall curvature. Still, the simplest explanation is that the universe is flat because it's infinite. Cosmic inflation, the rapid expansion of the early universe, naturally drives the curvature towards zero, and creates a region so large that our observable bubble is just one minuscule patch. Inflation doesn't guarantee infinity, but it makes an enormous, possibly unbounded universe very likely. Another clue comes from temperature fluctuations in the cosmic microwave background. These tiny variations have a statistical distribution that matches predictions from inflation. If inflation really happened, and the evidence strongly supports it, then the universe grew from something microscopic to something far larger than anything light can cross in 13.8 billion years. The part we can see is an impossibly small slice of the whole. In an inflationary universe, the observable region isn't special, it's just the area we have time to access. There's also the fact that we see no unusual patterns at the cosmic horizon. If the universe had an edge not too far beyond what we can observe, you'd expect some sign of it. Maybe an asymmetry in the cosmic microwave background, or an unexpected temperature gradient, or an odd variation in galaxy clustering. We don't see any of that. Everything looks too smooth, too consistent, too well behaved. This strongly suggests that whatever lies beyond our horizon is more universe. Not a boundary, not a void, not a wall, and not some exotic realm of different physics. Now, you might wonder whether the universe could be infinite but still vary in places we can't reach. Maybe there are regions where physical constants differ. Maybe gravity behaves differently. Maybe galaxies form differently. These ideas show up in speculative theory, especially in models where inflation happens multiple times in many locations. But none of that has observational support. As far as we can tell, the beyond looks like more of the same. There's a twist here, though. Every passing moment makes the observable universe larger, but that doesn't mean we'll see regions infinitely far away. Because expansion is accelerating, distant space is racing away faster than light can ever catch up. So even though time moves forward, new regions don't automatically come into view. Some areas may forever remain beyond reach, not because they're too far for now, but because they're permanently outside our ability to receive information from them. This gives rise to a strange idea. The truly observable universe, what humans will ever be able to see, might be smaller than the theoretical limit. Some galaxies visible today may eventually slip over the cosmic horizon due to accelerating expansion. They won't vanish instantly, but over extremely long timescales, their light becomes too stretched out to detect. Future civilizations might look up and see fewer galaxies. not more. This creates a kind of cosmic irony. The universe gets bigger, but the amount we can know about it gets smaller. Another interesting wrinkle is that while galaxies continue to drift out of reach, the early universe will remain permanently visible. The cosmic microwave background won't disappear. Its wavelength will stretch, becoming colder and harder to detect over trillions of years, but the signal from the early universe stays inside our horizon. That's because that light is already here, bouncing around inside our observable bubble. If someone billions of years from now tries to study the big picture, their experience will be radically different from ours. The universe will look emptier. Large-scale structure will thin from their perspective. Whole clusters of galaxies we see today will no longer be visible. They'll live in a shrinking observational footprint of a vastly larger universe. Yet the universe itself keeps expanding. This future scenario highlights the difference between the observable universe and the actual universe. What we can study isn't a full map of the cosmos. It's a snapshot constrained by light, time, and expansion. Beyond that snapshot, the universe could be enormous. How enormous? There's no upper limit. In many inflation models, the universe is effectively infinite. Even if it's finite, the numbers involved are so huge they break intuition, trillions of times larger than the observable region or more. But here's a subtle point that people often skip. Even if the universe is infinite, the number of different things in it might be limited. With a finite set of physical laws and a finite amount of information that can fit in a region, you eventually run into repetition. In an infinite universe, there could be faraway regions that are almost identical to ours. That doesn't mean multiverse doppelgangers in a sci-fi sense, it just means that in an infinite system of limited configurations, coincidences reappear. But this idea, while mathematically reasonable, sits deep in the realm of speculation, not observation. The main idea we can say with confidence is simpler. The observable universe is not the universe. It's a bubble carved by the speed of light in a universe that doesn't stop where our visibility stops. Everything we know about the cosmos, geometry, matter distribution, temperature patterns, expansion behavior, suggests the beyond is simply more universe, extending far past any distance we will ever be able to probe. And that's where the journey ends. Not because physics runs out, but because information does. The cosmos is larger than our ability to sample it, and that's not a failure of science. It's a feature of reality, a reminder that some structures are so big that even a universe full of light can't show them to us. Most of the numbers we deal with in daily life are small. Even the biggest ones, like the distance to another city or the time it takes to finish a school year, still fit inside a mental box we've carried since childhood. But the moment we try to scale that box up to the universe, everything goes sideways. Our intuition collapses. Distances stop feeling like distances. They turn into strings of digits that don't mean anything. A light year is one of the first places where this happens. On paper, it's simple. It's the distance light travels in a year. But light moves so fast that the number feels fake. Our minds never evolved to picture anything like 9.46 trillion kilometers. We can imagine a road trip. We can imagine a continent. We can't imagine a beam of light sprinting non-stop for 12 straight months. So today we're going to unpack what a light year really is, why it breaks our sense of scale, and what happens when you stretch that idea across the Milky Way and out into the deep universe. This is where distance stops behaving like distance, and where our normal mental tools finally run out. A light year sounds simple until you try to feel it. The human brain evolved to handle walking distances, not cosmic ones. We have tools for imagining a tall building, a long tunnel, maybe even the span of a country. But light doesn't move in human-sized increments. It races around Earth 7 times in a single second. If you tried to imagine a road long enough for a light beam to run for a year, you'd be imagining something longer than every road on Earth combined, multiplied by millions. This is why people ask why we don't just use kilometers. The problem is that kilometers stop being useful when the numbers get too big. If you describe the distance to the nearest star as about 40 trillion kilometers, the number collapses into abstraction. A light year at least carries a physical story in it. A beam of light moving as fast as physics allows, uninterrupted, for an entire year. But the real difficulty isn't the unit, it's our limited mental toolkit. We build intuition from lived experience and nothing in daily life resembles the scale of a light year. That's why even astronomers rely on analogies. Not because the concept is hard mathematically, but because it refuses to fit into the brain's built-in scale system. Understanding light years means accepting that your intuition will fail, and that's okay. Most of the universe exists on scales no brain was designed to handle. The speed of light isn't just fast, it's a limit built into the structure of reality. When something moves at that speed, it isn't just outrunning your imagination, it's acting out the tightest rules physics allows. That's why light becomes such a useful ruler. It's not arbitrary, it's tied to the geometry of space-time. When astronomers measure distances in light years, they're not trying to sound dramatic. They're tapping into the most consistent clock the universe offers. A photon travels at a constant speed everywhere. It doesn't need fuel, it doesn't slow down, it doesn't care about local conditions, it just goes. This gives us a shared yardstick that works across cosmic history. When you see something 10 light years away, that means its light has spent 10 years crossing the universe to reach you. There's no way to fake that. Light is the most honest messenger we have. But here's the twist. While photons follow straight lines locally, the universe they move through doesn't stay still. Space itself expands. That stretching changes the meaning of distance traveled. A photon might leave one galaxy when it's a few billion light years away, but by the time it reaches us, the space between has grown to many more billions. So a light year isn't a simple mile marker. It's a distance tied to the history of the universe's growth. Humans handle tens, hundreds, maybe thousands easily. Our intuition buckles somewhere near millions. But the universe doesn't stop at millions. It deals in quadrillions. The Milky Way alone is about 100,000 light-years wide. That's 100,000 years of uninterrupted light travel just across one galaxy. Try to picture that, and your mental image probably snaps. You either shrink the number until you can manage it, or you leave it vague and blurry. That's normal. 100,000 light-years is too big to visualize with the same clarity as a bridge or a mountain. Even professionals don't see these distances in their heads. They think in relationships. How long light takes to move, how objects interact, how signals stretch. The problem isn't that we're bad at math. The problem is that evolution gave us brains optimized for survival on Earth, not for navigating a galaxy. We're trying to use hardware built for daily life to reason about a universe trillions of times larger. The only way to handle these distances is to accept that intuition won't follow you. You rely on what the physics says, not what your mind can picture. When you hear that the Milky Way is 100,000 light-years wide, the number sits in the mind like a vague blob. So let's anchor it. If the solar system were the size of a dollar coin, the Milky Way would stretch for thousands of kilometers. You wouldn't even see the coin on that map without a magnifying glass. That's how tiny our solar system is compared to our galaxy. And yet, that 100,000 light-year diameter is only the visible disk. The Milky Way's halo, its extended cloud of old stars and dark matter, reaches far beyond that, stretching hundreds of thousands of light years. The distances are so enormous that even traveling at light speed, you'd need hundreds of human lifetimes just to cross our corner of the galaxy. What makes this scale even harder to grasp is that we live inside it. When you're inside something huge, you lose all sense of the boundaries. It's like standing in the middle of an ocean without seeing land. The size becomes conceptual, but the numbers are real. Every photon that crosses the galaxy is performing a journey so long that it would outlast entire eras of human civilization. People sometimes imagine stars in the galaxy lined up like street lamps. In reality, space between stars is enormous. The nearest star system to us, Alpha Centauri, is about 4.37 light-years away. That might not sound too bad. 4 light-years isn't a big slice compared to 100,000. But 4 light-years is still 40 trillion kilometers. If the sun were a basketball, the nearest star would be thousands of kilometers away. Signals we send and receive have to cross those absurd distances. If you were on a planet around Alpha Centauri and called Earth, your hello would arrive 4 years later. The response would take another 4. That's the consequence of living in a universe with such roomy spacing. Travel between stars isn't like flying between cities. It's like trying to cross a continent on foot while the continent expands beneath you. Even within our neighborhood, stars are separated by distances so large that human intuition barely registers them. And yet this is the dense part of the galaxy. Other regions have even more room. The space between stars isn't empty, but calling it thin is generous. On average, there are just a few atoms per cubic centimeter. You could take a single breath of air and find more molecules in it than in a region of interstellar space the size of a planet. What makes this interesting is that even with so little matter, the total distance is so big that the tiny traces add up. Clouds of interstellar gas can stretch for dozens or hundreds of light years. They can block light from distant stars, compress to form new stars, or leave chemical fingerprints for astronomers to study. But the vast majority of interstellar space is so empty you could travel for a year and hit almost nothing. This is part of why distances feel unreal. We think of space as an abyss, but the scale is so huge that even almost empty becomes interesting when stretched across hundreds of trillions of kilometers. The solar system feels large when you picture planets and orbits, but that feeling evaporates when you place it inside the Milky Way. The entire planetary region occupies a space less than a light day across. The Oort cloud, the remote comet reservoir, might stretch close to a light year if you include its farthest outskirts. Even then, the whole thing is smaller than a pixel in the Milky Way. This mismatch is the source of many misconceptions. People imagine galaxies as large versions of solar systems, but galaxies aren't collections of stars in tight orbits. They're vast rotating systems where most stars never come close to each other. If the Milky Way was scaled down to the size of a town, stars would be grains of dust separated by kilometers. Our solar system occupies one patch of one arm of one galaxy among potentially trillions. And yet it contains everything humans have ever known. The scale difference is so extreme that trying to visualize both at once is almost impossible. Inside our galaxy, distances grow so fast that light years start to pile up like loose change. The galactic center is about 26,000 light years away. That number hides more than it reveals. If you launched a beam of light today, it would reach the center around the year 28,000, long after every building, city, and government on Earth has vanished. Even moving between spiral arms involves leaps of thousands of light years. These aren't distances you cross, they're distances you observe. That's one of the fundamental shifts astronomy forces. Humans evolved to move through our environment, but the universe is too big to traverse. It can only be studied from afar. And yet, despite being locked into our small vantage point, we've mapped a huge fraction of our galaxy using light from stars, gas clouds, and dust lanes. By watching how stars move, by measuring their brightness and spectra, we reconstruct a structure too big for any species to ever walk through. Beyond the Milky Way lies a region called the intergalactic medium. If interstellar space is thin, intergalactic space is almost nothing. The separation between galaxies in our local group spans millions of light years, and between galaxy clusters, the universe becomes even emptier. The nearest major galaxy, Andromeda, is about 2.5 million light years away. When we see it, we're seeing it as it was before humans existed. It's racing toward us, and in about 4 to 5 billion years, the two galaxies will merge. But even that event is misleading. The stars won't collide. There's too much space between them. The galaxies pass through each other like two huge clouds mixing slowly over billions of years. Intergalactic distances change the rules of intuition. You stop thinking of objects. You start thinking of structure, clusters, filaments, voids. Light years aren't big units out here. They're the only units that make sense. Our galaxy isn't alone. It shares space with dozens of smaller galaxies inside a region called the local group. The whole thing spans about 10 million light years. The Milky Way and Andromeda dominate it, each with their swarm of dwarf galaxies. Over time, the local group will merge into a single giant elliptical galaxy. Outside the local group lies the Virgo supercluster, a region stretching over about 100 million light years. And beyond that is the larger scale structure of the universe, web-like filaments of galaxies woven through enormous voids. The sizes get so large that even light years struggle to keep up. At these scales, gravity binds galaxies into larger systems, but the expansion of the universe pulls those systems away from each other. Gravity wins locally. Expansion wins globally. Light negotiates between them. Cosmic voids are enormous regions, tens of millions of light years across, containing almost no galaxies. They're not holes in the universe. They're part of the universe's natural, large-scale pattern, shaped by how matter clumped in the early cosmos. What makes voids fascinating is how they distort our sense of emptiness. We think of emptiness as small, a gap, a pocket, an absence. But voids are vast. If you placed the Milky Way inside one, it would be alone for tens of millions of light years in every direction. That kind of emptiness feels wrong because we don't experience emptiness on scales that dwarf entire galaxy clusters. Voids help explain why galaxy filaments look like cosmic architecture. Gravity amplifies tiny early differences. Some regions gain matter, others lose it. Over billions of years, the universe stretches these differences into its large-scale shape. Zoom out far enough, and the universe stops looking like stars and galaxies. It starts looking like a cosmic web. Dense filaments connect clusters of galaxies. Those clusters surround voids. When you map them, the universe resembles a 3D foam. This structure covers hundreds of millions of light years. At these scales, you can no longer think of space as empty. It's dominated by patterns driven by gravity, shaped by initial conditions in the early universe. Even though the distances between nodes of the cosmic web are too vast to imagine individually, the pattern as a whole follows simple physics. You're not meant to picture each light year at this scale. You're meant to picture the structure they form. Light years become pixels. And the pixel count is enormous. Whenever you look at a distant galaxy, you're looking into the past. If a galaxy is 10 million light years away, you see it as it was 10 million years ago. If it's a billion light years away, you see a snapshot of a universe where Earth's continents were in different places and mammals were young. At extreme distances, you see galaxies in their infancy, small, chaotic, full of rapid star formation. These aren't slow-evolving objects. They're caught in the middle of building themselves. The deeper you look, the younger the universe appears. Not because the universe changes in the moment you observe it, but because you're sampling ancient snapshots stretched across expanding space. The farthest galaxies we can see sit at distances so great that their light left when the universe was less than 1 billion years old. This time window effect is one of the most powerful tools in astronomy. The universe gives us old pictures whether we want them or not. The universe isn't just expanding, it's accelerating. That means the space between distant galaxies grows faster as time goes on. This behavior comes from something called dark energy, a form of energy tied to the fabric of space. Acceleration has a strange consequence. Some regions of space move away from us faster than light. That's not a violation of relativity because the galaxies aren't traveling through space faster than light. The space between us is stretching. Over enough time, this acceleration will push many galaxies entirely out of view. Even light can't keep up with the expanding distance. They aren't leaving the universe, they're leaving our observable bubble. This is where the limits of light years become painfully clear. Expansion creates distances so big that not even light, the fastest thing in the universe, can bridge them forever. As space expands, it stretches light traveling through it. Longer wavelengths mean lower energy. This is redshift. A galaxy's redshift tells you how much the universe has expanded since the light left. Redshift isn't a Doppler effect from galaxies moving through space. It's a stretching of the light itself because the space it travels through has expanded. This is how we know the universe has grown dramatically over 13.8 billion years. The deeper we look, the stronger the redshift. It's a ruler encoded in the light, telling us how much stretching happened. It's also why distant galaxies look dim and red. Their light has been stretched over billions of years, drained of energy by the expanding universe. Redshift is one of the most important tools in cosmology. It's how we map the universe's history, not just its structure. Eventually, as you look farther out, individual galaxies fade into a uniform background. This is the cosmic microwave background, the oldest light we can see. It was released when the universe was about 380,000 years old, after the early plasma cooled enough for atoms to form. That light has been stretched from visible wavelengths into microwaves. It carries an imprint of tiny temperature variations, small fluctuations in density that later grew into galaxies and clusters. When we study this background, we're not just looking at distant light. We're looking at the universe before stars existed. This is the closest thing we have to a baby picture of the cosmos, and it forms the outermost shell of the observable universe, not because it marks the edge of space, but because it marks the earliest time when light could travel freely. This is where intuition finally breaks. The The universe is 13.8 billion years old, but the observable universe stretches 46 billion light-years in every direction. That mismatch happens because while photons traveled toward us, space itself expanded. The region where the light started is now much farther away than it was when the light left. So the observable universe is not 13.8 billion light-years across. It's about 93 billion light-years across. Not because light went faster than light, but because the fabric of space kept stretching during the trip. This is why the observable universe is a horizon, not a boundary. It's a limit set by time and expansion. If the universe stopped expanding, our visible bubble would grow steadily as more light arrived. But expansion is accelerating, and that makes the horizon dynamic and complex. People often picture the Big Bang as an explosion in empty space. But the Big Bang didn't happen in space. It happened as space. It wasn't matter flying through a void, it was the void itself expanding. That's why there's no center. Every point sees every other distant point moving away because space stretches everywhere. It also explains why galaxies don't fly apart locally. Gravity holds them together even as the universe grows. Expansion only dominates on huge scales where gravity is too weak to keep things bound. Once you drop the explosion idea, everything makes more sense. Redshift, acceleration, superluminal recession, the uniformity of the early universe, and the lack of any physical edge. The universe doesn't expand into anything. It expands by enlarging its own geometry. This number feels impossible until you realize that distance in cosmology isn't static. While light crossed the universe, space grew underneath it. Imagine walking across a room that doubles in size while you're walking. You'd cover more total ground than the original width of the room. That's what photons experience. The cosmic microwave background offers the clearest example. When those photons were released, the region they came from was much closer. Over 13.8 billion years of travel, that region has been carried outward by expansion and now sits about 46 billion light-years away. This is why the universe you see is always a younger version of the universe you inhabit. It's also why maps of the cosmos are really maps of time as much as space. The observable universe is a bubble carved by the speed of light and the history of expansion. It is not the full universe. Everything we know, physics, geometry, structure, suggests that space continues far beyond the 46 billion light-year limit. It may be hundreds of times larger. It might be infinite. Now, we can't see past our horizon because the light hasn't had time to arrive. And because expansion is accelerating, some regions will never come into view. They aren't missing. They're simply too far and receding too quickly. If the universe is flat, and measurements strongly suggest it is, it might stretch forever. If it's curved, the curvature radius is so large that the universe is still far bigger than anything we could ever observe. The cosmos is almost certainly larger than our visible bubble by a factor that breaks every intuitive scale the brain has. And that's the final lesson. Light years don't break our brains because they're complicated. They break them because they force us into scales we were never built to imagine. Yet here we are, mapping a universe that dwarfs every natural human intuition. Watch the next video.